Okay. So Phil, put your seat down, sit on it. Okay, we'll make a start now. So, good morning, everyone. Good morning. Can you all hear me? Yep. Okay. Good morning to those joining us via webinar. I hope you can hear me loud and clear. So, it's great to welcome you to this BEIS Nuclear Innovation Programme Supplies Day event today. My name's Ray Chegwin. I work for the Knowledge Transfer Network at the KTN, where I lead our activities on nuclear. I'm joined today by Natasha, who you would have met at registration, and also Chris Bagley at the back. Chris, hand up. Yeah. So those of you joining by the webinar, so use your chat function, say hello to Chris, and type in your questions, and we'll try and get to them as we go along. Before we kick off today, just the usual housekeeping. There's no fire drills scheduled today, so if you do hear bells, either go down the stairs the way you came in, do not use the elevators, go down the stairs. There's more exits if you come up this room and go down the corridor to the right. Make your way outside, and we congregate on the island, the Tony Hancock statue. So that should be fine. Facilities, there's some gents, ladies down the corridor, again down to the right, and there's some just outside where we came in. We will be having coffee just where you had it outside at the coffee breaks. Lunch will be on level 1 on the first floor, so just down one there for lunch. Other than that, please, you have a Wi-Fi code there at the front, so those of you can see it, but mobile phones, please, either switched off or to silent. Apologies to those who are joining us by webinar. You may not have, or you will not have, all of the slides. So sorry about that, but all the information, links to all the slides and information will be sent to you following the event, so you'll all have copies of all the slides that are presented today. Brief run through the agenda. Once I've finished, I'll hand over to Cy Dilks of BEIS, who'll give you a bit of a history and talk about the day. Then we move on to the first round of an update on the projects to date from Wood and Fraser-Nash. There'll be time for Q&A after each session. We have a room full today, and it's going to be quite tricky. Can I just remind you, and I'll try and remember again to say at the time, but Q&A, please wait for the roving microphone to come to you, because again we need to record this and capture all your questions and comments. Natasha will come round with a roving microphone. It may take some time to get to you, but we'll do our best. Then we'll have a very short break, and the short break will be get outside, comfort break, grab a coffee and come back inside again. And then we'll make the first announcement, fingers crossed, about the next IT for the Advanced Reactor Design Phase 2. Q&A again, and then a brief overview from NNL on their project before we break for lunch downstairs. This afternoon session, you'll hear a lot about the progress on the Advanced Manufacturing Materials Phase 1 projects from Wood, University of Sheffield, Fraser-Nash, Nuclear AMRC and Camel Lead. And then we'll go on to hear about the second sort of opportunity, the grant call for the next phase for the Advanced Manufacturing Materials call, followed by Q&A. And then we basically stop at 4 o'clock. Plenty of time for you to carry on having another coffee and networking outside. The event formally finishes at 4:45. So that's it from me. Again, apologies. The next session then, I don't think there's any slides for the webinar, but I'm handing over to Cy now, he said. Oh, there it is. Yeah. Hi, say hello to my family. I've lost my cursor. Has anybody seen my cursor? Oh, great. Well, why isn't it on here? Oh, it's going ever so well. Which way?
Shift it to one of the sides. You've gone on to extended screen. There you go.
Oh,
There you go.
fantastic. Brilliant. Hey. Seamless.
Good morning, folks. So my name's Cy Dilks, and I'm the head of Nuclear and Renewable Innovation at BEIS. So the plan for this quick session is just to do a bit of context setting of where we are in terms of the whole Nuclear Innovation Programme, what we've done so far, what we're doing at the moment, and what we're going to do next. Now, there is way more information on these slides than you can take in the short space of time we have. So the idea is that you can then read them through at your leisure. So, what we've done so far. So phase one launched back in 2015-2016 and looked at about £20 million over 5 initial work streams, drawing on the original themes that we had taken from the advice of the NIRAB recommendations. Phase two we kicked off in November of 2017. January 2018, and that was a couple of extra work streams looking at safety and security, nuclear fuels and reactor physics, and we launched the first stage of the Advanced Modular Reactor Feasibility and Development Programme. So phase three is the focus of today. So I've got a lot of these. I'll kick through the main ones. And the writing is so small that you're not going to be able to read this at the back, so apologies now. So, kick off with the ones that are relevant to this morning. This is the digital nuclear reactor area of the work, and on virtual engineering, we kicked off a program back in 2016. Which was taken forward by a consortium led by Wood Group, and that looked at the nuclear virtual engineering capability of the UK and the ability to sort of develop modelling and simulation. That piece of work comes to the end of its phase in March this year, and Wood are going to give you an update on where they are so far. We launched an invitation to tender back in December for the next phase of this piece of work, and again, we're going to come back to the details of that later today. Then we have thermal hydraulics. This is also included in the invitation to tender that we're discussing today. And again, we kicked that back off in 2017. Fraser Nash have been leading a consortium there, mostly around developing specifications for a thermal hydraulics facility and modelling and simulation capability in the UK. And again, there's a separate theme on there that is developing the £40 million thermal hydraulics facility that the ministers have announced for North Wales. Then we get on to advanced nuclear fuels. Again, first phase of this was mostly done by National Nuclear Laboratory. This morning they're going to give you a quick rundown of where they've got to. And the next phase of that, and the slide that I'm going to come to next on recycle, we're currently in discussions with National Nuclear Lab to work on them leading for us on a national programme of fuel cycle for the next bit. That hasn't been determined yet, but we're still in negotiations and discussions on how we can get NNL to sort of lead a programme going forwards. And part of the discussion you might want to have over lunch today, after NNL have done their presentation, is on how you can get involved with that. So again, fuel recycle and management. NNL took forward a process on aqueous reprocessing back over the last few years. That concludes in March this year, and we'll be taking forward a programme afterwards. Point of this afternoon is advanced materials and manufacture. We launched a range of things back in 2017. There was a small business research initiative that we launched with Innovate UK. And that took us into a process where we had 5 successful applicants going forward over the last year and developing techniques and technologies that would help in either advanced manufacture or the materials behind that. And again, this afternoon, you're going to hear from each of those successful applicants on what they've been doing before we launch the next phase of that process, which is a £20 million grant call. forgot to mention, everything I'm saying today, particularly about the grant call going forward, is subject to us having a government from tomorrow. So we're launching stuff today, and we're getting stuff out as soon as we can this week, but I have no idea what's going to actually happen for the rest of the week, so I'm basing this on a predication that everything is fine and we're carrying on. We then have nuclear safety and security engineering. Fraser Nash are taking this forward for us at the moment, and we have a final phase which will kick off next year. And then just to whistle through the last few, this is the Nuclear Facilities and Strategic Toolkit phase. It's a fairly small one. It's a miscellany of operation tools, of knowledge capture from Doon Ray, and various other bits and bobs, and a National Nuclear Lab undertake that for us. Again, just to give you a bit of an update on where we are on the Advanced Modular Reactor Programme. That kicked off last year. We've had 8 organisations literally running hell for leather over the past few months, preparing feasibility studies and research plans. Those all come in, I believe, tomorrow, 15th of February, 15th of January. We will then go through a process of evaluating them and doing a down select, and in July-ish of this year we'll announce the winners of that, and they'll take forward a second phase of research and development. Again, you've got the names up on the board there. So to finish off my bit, which might be slightly earlier, but then we can pile on. Phase 3, what we're looking at today. It's the final tranche of the spend. There's around about £180 million if everything comes together and everything works. It's made up of a number of different pieces. 3 of them you're here to discuss with each other today. We've got the Advanced Reactor Design. Lots 1 and 2 are just about to come up. We've got the Advanced Manufacturing and Materials Grant Call, which we're going to deal with this afternoon. We have an Advanced Nuclear Fuel Cycle that NNL are going to give you a little bit of a talk about. And then things coming up later this year and in the next year, Thermal Hydraulics Facility, UKAEA are working with us to potentially launch procurements in spring, summer of this year, still subject to some final business cases between us and the Welsh Government. Advanced Modular Reactors, as I said, that's going to kick into its next phase in summer of this year, and hopefully we're going to see up to 4 organisations receiving up to £10 million to take forward some reactor designs, obviously not to build, but to get them closer to commercial development. And then there's a final section on safety and security that we're looking to launch end of this year. And that, I think, is everything for me.
Thanks very much, Sam. Now, assuming I can find my cursor again. Bum, 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 bum. There you go. Okay, I'd like to invite Ahmed from Wood. That's why Si finished early.
Good morning, everybody. Delighted to be presenting progress on integrated nuclear digital environment on behalf of the consortium. This was meant to be it still is, a joint presentation, but I'm afraid to say Dave Bowman of VEC wasn't able to make it. I knew something wasn't quite right when he dialed in from bed in our last meeting, so wish him all the best. So I'll hand over to Mark for the first few slides, and I'll come in a little bit later for the later slides.
Okay, thank you. Good morning, everybody. So I'm going to talk a bit about the Digital Reactor Programme as it stands at the moment. First of all, I'm going to go through the context and some of the history, and then through the vision, and then hand over to Ahmed, who's going to talk a bit about the progress that we've made to date. So So the whole purpose of digital reactor design is to try and deliver a culture change across the industry through enhanced collaboration, using, and we believe we can do that by providing digital tools in an integrated collaborative platform, which will allow us to exploit the benefits that we could obtain from industry, concepts such as Industry 4.0. And from that, we can both look to reduce costs and also increase value to the nuclear industry across the life cycle. And this is all about trying to get the UK nuclear industry the tools to address the problems that we face at the moment, with looking to rebuild the nuclear industry such to the point that we can actually start to compete internationally in areas such as reactor design, to both to deliver revenue for the UK, also sustain and grow jobs. So what we're talking about here in terms of the vision is to provide what we'd like to think is nuclear engineering for the future, where we can actually use digital technology to enhance engineering by bringing in not just the traditional disciplines of engineering, such as computer-aided design, for example, but also bringing in simulation that we can draw down from our experience in, for example, in reactor physics and also in materials chemistry, for example, to actually get to the point where we can have a platform which allows us to do in silico simulation of nuclear design concepts. This will allow us to deliver results faster. And later on, we'll talk about some of the use cases that we've developed, which actually show us how we can actually deliver improved performance very, very quickly by actually just integrating existing work streams together. It will allow us to improve our decision making by having easily auditable decisions. Easy auditable decisions where actually we can actually start to make decisions on a strategic level based on information that we gain from a lower level, so higher fidelity information, so we can make decisions based on confidence rather than guesswork. We want to be able to start bringing in new technologies. So most of you have probably seen a lot of the hype and excitement around digital technologies such as AR, VR, etc. Various other technologies will appear and disappear over the next few years as people try to understand which one of those are actually useful. But we will develop the technology to enable to use the ones that do prove to be useful and help us to do the work. The next point which we're looking to develop as well is actually to take the simulation capability that we'll develop in this platform and actually link it into the real world. And that's through the development of what you could call digital twins, where I can actually take the computer simulation, couple it to the real world asset and potentially a real-time acquisition of data to monitor the performance of the system real time throughout the service lifetime and take it forward. And that will give us that end-to-end integration for the design and licensing of the future nuclear plant. So the concept for this project came from something we developed at NNL and the University of Liverpool a few years ago, called Integrated Nuclear Digital Environment. And the idea being that if you consider the life cycle of nuclear systems, it could be a reprocessing plant or a nuclear reactor, it doesn't really matter. We go through several phases, through physical tests, operational units, end of life through POCO, which many of the UK facilities are going through now, through to the decommissioning of those facilities and the storage of some of those materials and eventually geological disposal. What we want to be able to do is create a parallel digital world that represents each one of those stages in the life cycle. And this is the first, I suppose, dimension of the integrated nuclear digital environment, with the idea being that the physical tests were replicated in virtual prototypes, the operational asset were replicated in digital twins, etc., down the list. And feeding into that, we have the ability to bring in data from multiple sources to actually populate that environment and make decisions upon it. There are many different benefits from that, several of which I've covered off in the first slide, which can be gained at each point in that digital environment. For example, having better virtual prototypes is what gives us the ability to do in silico design, for example, to faster, better, more optimized designs. The digital twin, that's what we're targeting towards delivering the cost savings and perhaps hopefully as well increased value for the nuclear industry across the operational lifetime, potentially to bring these technologies in to help with assets that we already have in operation, such as AGR, for example, to do things like lifetime extension, etc. decommissioning, replica, future decommissioning costs, etc. So just again, emphasise increased value, reduced time, greater certainty of delivery in time and costs, and finally as well, collaboration towards a common goal. And one of the advantages of creating this digital world is we can create a system where all the data can actually be managed together, and people can collaborate within this virtual environment right across different organisations to bring the industry together. And one of the opportunities we identified fairly early in the phase 1 programme was actually the ability to, in a digital sense, create that end-to-end integrator that doesn't exist in the UK space at the moment. So there is no Ariva, EDF, whatever, Hitachi in the UK space. We could actually create one by having a marketplace, which is a virtual environment which can actually deliver that end-to-end integration. The second part of the indie picture is the multi-scale and multi-physics dimension. And that's the idea being where actually, well, the nuclear industry has been operating for many years, and we've actually developed a fantastic amount of knowledge about how nuclear systems operate, but we don't use it effectively. And what we'd like to be able to do is integrate all of that fantastic knowledge in with our decision-making capability to actually take the nuclear industry to the next level. And that means taking system engineering principles and modelling down the scale from the plant down to the component to the subcomponent, down to even the microstructure of the nuclear fuel, for example, to actually provide that high fidelity information. And we have such great knowledge, we can start to use that within the digital environment to actually improve the quality of decisions that can be made by actually having more certainty on the predictions. So the next bit, so joining the dots. So I've talked a little bit about some of the opportunities there. So here's something a bit more about the specifics. So in integrated reactor simulation, for example, we could be talking about integrating neutronics, thermal hydraulics, and structural simulation together to create a whole description of all the different physical processes that exist in the nuclear reactor. We can bring in data-centric engineering, so we can link in mechanical engineering, which would follow on from the integrated reactor simulation, for example, in together with civil simulation and instrumentation and control around the idea of the digital twin concept, which then we can link through digital twins into areas such as BIM, for example, where we can bring the information together into one platform, help with construction planning, and also enhance the ability to e-work. Another key aspect of this programme is we actually see this programme as a means also to integrate all the other programmes within the NIP programme together. Because this is a programme about bringing information together, not necessarily about creating the information in the first place. So we can look at bringing in, for example, the opportunities we've got from the thermal hydraulics, for example, to improve and enhance our ability to understand and simulate those systems. We can bring in advanced fuels, for example. The idea being that we could use information from the Advanced Fuels programme to virtually test what an advanced fuel concept would actually mean in terms of, for example, existing PWR fleet, for example, or some other advanced reactor concepts. We're looking, when we have been looking across the programme, to establish links with various other organisations which are leading those respective programmes. For example, the North Wales Thermal Hydraulic Facility, and also we've been talking with UKAEA about how we can actually link this in with the needs for fusion, which are very different to fission because they're in a very different part of the life cycle. But ultimately, a lot of the technologies could be interchangeable. And so there's definitely some opportunity there. Also the AMR program, SMR program for AMR, we see this as potentially a fantastic opportunity for them to actually use digital tools to actually help them get their business case through, which is always a challenge for anyone coming with a new idea, is how to convince somebody your idea is sound, and the more information that you've got, the increased confidence that investors will have that in that decision is sound. Okay, so finally from myself, before I hand back over to Ahmed, who's going to be talking about the progress. So I just wanted to illustrate some of the highlights that we've actually achieved in this phase 1 of the programme. First of all, we've developed an engagement plan. We've had a number of events where we've actually demonstrated some of the technologies. We'll show you in some of the later slides. We've also had meetings where we've spoke to industry experts and they've told us what they want. And we've taken that on board and built that into the programme of work in terms of industry capture. We've started to clarify some of the end user requirements in terms of different capabilities. Well, we've created a vision here which means all things to all people, or some things different to different people. So we have a lot of competing demands to actually focus on within the roadmap that we actually now produced. We've developed some test cases to prove concepts, which we'll show you a little bit about in the following slides. Which is, and they've been developed just to really show just how feasible this technology is and how we can adapt it for the future. Part of that has been integrating simulation codes within Indy, because that's something that hasn't been achieved substantially within the UK research space before. So we've managed to do that for excellent work that's been delivered by the University of Liverpool, involving all of the different partners of this project who've contributed their codes to the demonstration cases. We've linked in with national facilities and high-performance computing, specifically the Daresbury STFC Hartree Centre, who've hosted some of our demonstration cases, for example. And we're also developing a security and safety roadmap on the use of this technology, which with the idea being to understand what the challenges are of actually having this collaborative environment where we have secure data being shared between multiple partners, and developing the roadmap for how we'd actually take that concept through to final product. And so finally, just a little bit about the events that we've had. We've had 4 capturing of events across the 2 years of the programme. We've had 2 public events where we've actually presented some of the technology, and many of you here have probably been to some of those where we've actually seen some of the demos using VR and also computer simulation of reactors. We've also had several integration sessions with various different stakeholders as well across the course of the programme. And then finally, in terms of international collaboration, in about a month's time, just like under a month's time, we're having a collaboration meeting with the US DOE around collaborating with the Castle program in the United States, which is developing advanced pressurized water reactor simulation technology, with the view to establishing how we might work together in research for the next near, mid and long term across those organisations. So I'd just like to hand back to Ahmed now, who will talk about the use cases and progress that we've made regarding the roadmap.
Now, the project at a technical level has presented many challenges. I would just like to share some of the design considerations that we've had to consider. Now, on the architecture design, there are many, of course this is not an exhaustive list, things like cold coupling, flexible meshing. The important one I want to pick out is switchable modules. Well, what does that mean? Well, it means that the ability to switch one code for an identical, another independent code. So important for independent verification and giving us the confidence in our analyses. Uncertainty analyses and the integration of codes. On the modelling side, we've had to consider obviously the reactor core, structural mechanics, cooling, fuel behaviour and so on. Information management, audit trails, very important to keep track of the data, about the knowledge that's coming in, and also the knowledge that is being generated within the digital environment. Of course, you've got plant data such as BIM and all of the other OPEX data. User experience. We are considering a simple to use user interface, designing that. User accessibility and visualization, very important elements in that. And we put in a fair bit of work already on those. Quality assurance, very important. Validation, verification, both QA for both framework and the users. Safety and security, data sharing, IP protection, again, very important. Some of the later slides will illustrate that. And of course, international considerations and international engagement is one of the very important aspects of this. Collaborative environment, that is the crux of it. This is what this digital environment is about. It's about collaboration, and the following slide will actually illustrate some aspects of that. Integration of other programs, of course, Marcus just talked about, and infrastructure. This slide presents the framework architecture. In this, we have the bottom bit is about a federation. We call it a federation, but that is actually an analysis. And there are many elements to a federation where you have number of codes linked. RTI stands for real-time infrastructure. So number of codes integrated via the RTI, and the running and the coordination is all taken care of in there. Recording of the results and interfacing with the external database and application of any uncertainty quantification, which is an external input. This slide actually illustrates beautifully what phase one has managed to achieve. This, as you can see, a number of independent organizations, if you like, at the bottom, who each are contributing their own IP, their own code system into this collaborative framework. We have the developer in virtual engineering, developer of the framework. So we've all managed to get together to run a real-life simulation using all these independent codes provided by different organizations, have come together to demonstrate that we can run a fast and reliable simulation to lower costs. And of course, it is a higher fidelity simulation. Never before, I don't think we've ever managed to do this. So this is a first, certainly in my 26 years or so in the nuclear industry. This is the first time I've seen such collaboration. Just a word about a roadmap of and our vision of where we want to go, both short term and in the long term. We have a number of goals and outputs along the way to a final beyond 2030 vision, where we think this will be the environment for nuclear design, development, operation, decommissioning. But along the way, we hope there's a continuous delivery of solutions into industry. So we're not saying it is 2030 by the time industry sees any benefit. In our 2-year vision, you can see the orange box there saying release 1.0 of the integrated technology demonstrator. And we hope at the end of that phase, we have a real working environment able to support real projects. Now, along the road, we have parallel programs, and our development does not depend on any of these program outputs as such, but we're able to integrate any output from those. For example, new codes development. As they are developed, we can take those on board. We have continuous engagement to ensure that we take on board all of the feedback from users. And we're able to integrate all of the other parallel-based programs and in readiness for supporting real-life projects, such as the thermal hydraulics facility and AMR, SMR designs, and so on. So in conclusion, the vision is ambitious, and it aims to bring cross-sector learning. INDI is designed and will deliver lower costs, facilitate lower cost of regulation, and it does support innovation, and as we've mentioned earlier, is aligned to Industry 4.0. Our approach targets early industrial uptake, so in the next couple of years, our digital environment will be ready to support real-life projects. So phase 1 has delivered a proven concept, and we've also defined some key factors for the coming phases. Just a last slide, a word on the team. The project has been more than just the development of a digital framework. We've worked with diverse organizations, and some of those are key partners like VEC are outside the nuclear industry. And that has been a major strength. There have been times where we've had to answer awkward questions, like, why are you doing it like that? Are you sure that's right? And it has made us think. So it has been a real strength. So being able to draw upon the expertise and experience of other sectors is a major plus. I think we've been inward looking for far too long. So a culture change, I know we've talked about that, but it's a necessity to enable the benefits of the development to be fully realised. That's some acknowledgements. That's it. Thank you very much.
Thanks to Ahmed and Mark for that presentation. Hadn't realised HPC was high performance computing. I thought of something else. And a small plug actually. Mark actually came. We also have a digital special interest group which resides in the Nuclear Institute. Myself and Philip Isgar, who's here today. Philip chairs that group. So Mark very kindly came to our last group meeting and gave an overview of the INDI project. So that was excellent. So if you'd like to hear more about that special interest group, then see me or Philip at the break. So now I'd like to invite Richard from Fraser Nash to give an overview of the thermal hydraulics R&D project.
Thank you. Okay, thank you. Good morning. My name is Richard Underhill from Fraser Nash Consultancy, and I'm here to go through the developments that have taken place on the Thermal Hydraulics Research and Development Programme Phase 1. So this is the other half of the Digital Reactor Research Programme. The aim of my presentation is to give you an overview of the work that we've done within Phase 1 of the Nuclear Thermal Hydraulics Programme. This is a 2-year programme that began in March 2017. I'll start by giving you an outline of the objectives and scope of work that we've done, and then describe some of the results and recommendations from the two core aspects of the work, the thermohydraulic test facility and the model development side, which are linked together. As I say, there are two core aspects to Phase 1, the National Nuclear Thermal Hydraulics Facility and the Thermohydraulics Model Development. As Si mentioned, the Thermohydraulics Facility is hopefully going to be built in North Wales, in Bangor, and potentially a budget of 40 million there. And within Phase 1, the aim is to specify that, and that's the start of the process. On the model development side, we're developing new models to help us collaborate and internationally get more involved in international programs. And the key is that these two aspects are linked together and need to be integrated together, so work as a whole to drive the country forward. And the key objectives of the programme are to increase UK participation and collaboration in international activities, and to increase the uptake of digital engineering practice. This will be achieved through improving UK predictive modelling capability and understanding, and improving the safety and understanding of through-life performance ultimately in reactors. This will be achieved by enhancing the way that nuclear design programmes are delivered, so that within the UK we can develop a highly skilled workforce to drive these designs forwards. And my particular area is obviously focused on thermohydraulics, which is a key part of the reactor performance, driving the heat transfer and the flow around the reactor core. Within the thermal hydraulics Phase 1 scope, this kicked off the work, looking at the test facility and the model development. Both programmes started with a critical review of the state of the art on both facilities and model development. On the test facility side, we're developing a specification for this National Nuclear Thermal Hydraulics Facility. What should it look like? How big should it be? What should it do? But also looking at how the opportunities were for using this facility to support the other programmes within the Nuclear Innovation Programme. On the model development side, again, we've got a specification for what model development should we be doing within the UK. What's important? Where are the key requirements for nuclear thermal hydraulics? But also kicking off some of that initial model development with innovative models to try and start this process off and kick the work off in modelling. As mentioned briefly earlier, Fraser Nash are leading the Thermal Hydraulics Phase 1 programme, and we've got a core team of 6 people. We've got the University of Manchester and University of Sheffield undertaking the research and innovative model development within the programme. We've got STFC involved for their parallel computing and CFD expertise. And we've got EDF Energy and Westinghouse involved from an industrial expertise and experience perspective to make sure that it is focused on what the industry needs and wants. I'll now go through each of these aspects of the programme and show you what some of the results and recommendations that we're making. Starting with a critical review. As I mentioned, there are 2 aspects to the review, one looking at facilities and one looking at model development. And the review of the test facilities, we've looked at all reactor technologies. So SMRs, light water reactors, but also all advanced reactor designs, all Gen 4 technologies. So gas, high temperature reactors and fast reactors, liquid metal, sodium and lead, and molten salt and supercritical water. And we looked at all the test facilities around the world and reviewed some of their capabilities. We also looked in detail at a few of these test facilities that have been operating successfully for 30 years to understand what their capability is, where their research focus is, and what their measurement capabilities are. This review highlighted that there was no real obvious gaps in the international test facility requirements. There's a lot of facilities out there in all types of reactor technologies. It also showed that the successful ones have a strong research focus, and they've developed their own measurement capabilities to generate high fidelity data. On the modelling review, this critical review was led by Professor Lawrence from the University of Manchester, with the support from a number of academics from both the University of Manchester and the University of Sheffield. This highlighted the wide number of challenges within thermal hydraulics and the large number of phenomena that are involved in terms of boiling, turbulent flow, turbulent heat transfer, and therefore the large number of challenges that still exist in modelling nuclear thermal hydraulics. It also highlighted the fact that computing power and artificial intelligence is increasing rapidly around the world, and there is growing potential and interest in using these high-fidelity tools for nuclear reactor design. And it's being researched and developed a lot around the world and internationally. And therefore, we've got an awful lot to do to catch up with that research. The next step in the process was to look at what the user requirements are for thermal hydraulics research and testing. So we undertook an end-user engagement process where we contacted a number of people from industry and academia through questionnaires and workshops. This included reactor developers, academic institutions, service providers, and the ONR. This highlighted the large number of user requirements that there were. And we took these requirements and split them into both experimental and modelling requirements. Some covered both and needed both experimental and modelling development. It also highlighted the differences between the technologies and the level of maturity between SMR's and AMR's technology. As a result of the user requirements capture, it highlighted the need for the quantification and bounding of uncertainty in CFD to increase trust by the regulators in using CFD and high-fidelity tools. But in order to do that, there's also a need for high-quality validation data. So high-quality experimental data to validate the models that we've got. And that will then help progress the reactor design activities and develop confidence in those designs. There are a huge number of thermal hydraulic phenomena out there that we need to investigate. Some of the ones where the UK is strongest and where the greatest need is around natural convection, two-phase flow, single-phase turbulent mixing, and fluid flow component fatigue. There are many others, though, that were highlighted as useful and required. We then took these user requirements and helped to use them to feed into the test facility specification and the modelling specification. So looking at the work that was done on the test facility side, we started by developing a test facility specification. This was developed from the existing facilities and also the user requirements. And it very clearly looked at the bounding parameters for the building itself. So how big does the test facility need to be? How high is it? How much area does it need? What power does it need? What strength of the floor does it need to be to accommodate the different reactor test facilities? We also need to accommodate BEIS's requirements for the facility. They want it to be flexible, to bound all possible test rigs that industry need, to be able to accommodate all advanced reactor technologies, and also, ultimately, to be self-funding. This is a very broad and demanding set of requirements, and not surprisingly, we've had trouble meeting them all. As part of the facility specification, we've also done a site assessment of the Menai Science Park, which is the current proposed location for the facility in Bangor. And the picture there shows the site of the Menai Science Park, with the site for the test facility itself in the top left-hand corner. We've also done an assessment on this site against the facility specification. So is the site capable of housing the facility? And identifying the benefits and limitations of the site. The next step was to look at how the facility can be exploited and also used by some of the other nuclear innovation programs. So we've developed an exploitation plan that explores some of the potential organisational structures that the facility could have, but also looks at some of the short-term and medium-term activities that you need to do to make sure that the facility gets used and is appealing to industry. As part of this exploitation plan, we've also looked at our vision for the facility. We believe that the facility should have world-leading nuclear thermal hydraulics experimental capabilities. It should lead the validation of new thermal hydraulic models. It should be an active part in developing and inspiring the next generation of thermal hydraulics experts and bring together academic and industry partners. And although the facility should have a focus on thermal hydraulics, it is also there to collaborate and be used by other nuclear innovation programs. And we believe some of the key areas that it could support is safety assurance and the testing of materials in reactor environments. So, what should the facility do on day one? I think the one thing everyone doesn't want is an empty building that has got no rigs in place. So we also looked at what should the test facility do on day one, and what should the research focus be, and the initial test rig that it should hold. And BEIS wants us to provide clear recommendations for our thoughts on what the facility should be, based on the user requirements, our independent assessment, and our judgment of what they should be. So we think that the facility should have an initial research focus around natural circulation and heat transfer. This area of thermal hydraulics is key to all reactor technologies. So it's got the broadest capability and the broadest application to the different technologies. We also think that it needs to have a novel measurement capability to make sure it stands out from other facilities around the world and provide the ability to take high quality, high resolution measurements that can be used for model validation, particularly at reactor conditions, which is where currently other test facilities are struggling to do. Based on these two areas, we think that the first rig in the facility should be a large-scale natural circulation, water-based test loop that ideally operates at reactor conditions, where we can get this high-fidelity data to then validate the CFD models for those types of flow. The other aspect is industrial investment. We need the facility to be self-funding, and we need the industry to want to use the facility. So how can we make it valuable and appealing to industry, to all reactor developers? Therefore, it also needs to have the space, capability, and flexibility to house and operate industrial test rigs. The other aspect that we need to cover is it also needs to be able to accommodate all advanced reactor technologies. Maybe not on day one, maybe in 10 years' time, but all potential Gen 4 technologies, we need to be able to have a rig in there. So ideally, the facility should be able to operate test rigs using high temperature gas, such as helium, which covers both the high temperature gas reactors and gas-cooled fast reactors. We also want the ability to undertake small-scale tests using molten salt and liquid metals, so that this will allow the UK to develop the skills and expertise in these difficult coolants and build the experience necessary to then take on a larger test rig in the future, using liquid metals, so sodium or lead or molten salt. As I just mentioned at the beginning, UKAA is now leading the design and build programme for this test facility. A workshop was held in Bangor on the 13th of November, where these recommendations were presented and tested with industry. And the business case is now being written and developed by UKAA to take this forward. That gives a bit of a summary on the test facility side. I now move on to what we've done under the model development process. So once again, using the user requirements capture that we did at the beginning, we held a 2-day workshop in April with over 30 members of the UK thermohydraulics community. This focused on 8 core areas for model development, looking at multi-fidelity, best practice and uncertainty evaluation, boiling and condensation, large-scale multi-phase flows, advanced fluids, multi-physics, turbulent flow and turbulent heat transfer. I'm sure there are other phenomena that other people are interested in, but based on the user requirements, they seem to be the most important to the UK as a whole. As a result of that workshop, we developed 34 research and development proposals with details of the proposed research and scope of work for each one. These were set at approximately one full-time engineer over about 3 years. This is a part of the research plan for Phase 2. And this provides a selection of ideas for Phase 2 and beyond. Unfortunately, there's far too many ideas to fund under Phase 2. So we did look at how we could prioritise and categorise. Because of the wide range of technologies, a wide range of different thermal-hydraulic phenomena, it's very hard to prioritise the research proposals. So what we've done is categorise them into different areas, focusing on reactor technologies and modelling technologies. Under the reactor programmes, we've looked at Gen 3 and SMR PWRs, Gen 3 BWRs, high-temperature gas reactors, liquid metal fast reactors, and molten salt reactors. On the modelling side, we looked at how these research programmes could improve value from UK modelling capabilities, specifically looking at two-phase water, support to structural integrity, heat transfer and passive cooling, and support across all Gen 4 technologies, and finally support to supercritical CO2 power cycles. The list of the 34 research proposals have been split into each of these technologies, and I've included them at the end of the presentation rather than go through each one now. But they are there for you to look at the end of the presentation. The other side of the model development was the initial development of innovative models. Within Phase 1, we had 4 core programmes led by the University of Manchester and the University of Sheffield. The first of these programmes, called Smart Component Models, was led by the University of Sheffield. This had a vision to develop a modern CFD-based sub-channel framework for nuclear reactor modelling, where you used a coarse grid CFD approach to model the whole reactor system, with the ability to embed more detailed CFD models where needed. This has the advantage that it can significantly reduce the computing cost compared to normal CFD and embed more detailed models easily into the overall reactor system. As part of this work, the baseline model has been developed and validated against 2D and 3D test cases. And the vision for this is that it can be applied to any reactor technology. It's not water or advanced reactor specific, and could allow the whole reactor to be modelled in CFD. This has been achieved using empirical correlations to model the near wall flow, rather than using a high fidelity boundary layer mesh. This reduces the mesh size by approximately 150 times, and therefore does give you the ability to potentially run a whole reactor simulation in reasonable timescales for the design process. The aim being that this can bridge the gap between the empirical codes at the moment, the systems and sub-channel codes, to modern best practice and beyond. Second phase of the model development looked at single-phase flow, particularly around water. We looked at a number of aspects of single-phase flow, one of them being natural convection in a loop. This was led by the University of Manchester, and we developed a simple basic loop with a heater on the bottom and a cooler on the side, and developed correlations for the flow physics involved. The next step was to develop CFD models to predict this complex unsteady behaviour. And that depends not only on the size of the heaters and coolers, but also on how the transient started. So what was the initial starting temperature? This is intended to address a key uncertainty in some of the current modelling methods around system codes for modelling this unstable natural circulation flow. The other side of this research looked at a completely different type of CFD modelling approach called smooth particle hydrodynamics, SPH. This methodology has been applied to free surface flows for a number of years, but hasn't been used on nuclear thermal hydraulics. So the University of Manchester looked at modifying and developing this technology so that it was suitable for wall-bounded flows. And they did this using a novel iterative shifting of the SPH particles to ensure that the flow calculations were accurate. This has been applied to a rod bundle flow case in single-phase flow and compared against the results for the normal finite volume CFD methods. This is a new and innovative way of doing CFD modelling for thermal hydraulics, and it could provide benefits in terms of accuracy and solution time. The third phase of development was around two-phase flow. There are many aspects of thermal hydraulic two-phase phenomena. This includes boiling, evaporation, condensation, and it was far too much to look at all aspects of those two-phase phenomena. So we focused on two-phase flow boil-off, looking at a rod bundle boil-off case, where the mixture front develops and travels down the fuel bundle. This leaves exposed fuel rod surfaces, which can have excessive temperatures and cause damage to the reactor. As part of this work, the University of Manchester found there was very little data on this around the world to validate the models against. So a new experiment was set up and run in the University of Manchester. This used high-speed cameras, wall temperature and void fraction measurements to get the data that needed for the CFD validation. These models are being run and validated against this new experiment. There's a lot of interest and research being done in two-phase flow around the world. This will help support that and develop new models to allow the UK to get more involved in this area. The final area of model development was around different media, or particularly liquid metals, which have a very low Prandtl number compared to air and water. The University of Sheffield started by retrieving experimental research carried out by the University of Manchester in the 1980s, which had a sodium pool and a cover gas region with argon, looking at the aerosol transport and convection within that domain. There were two areas where we looked at in this area. One was modelling of that cover gas region above the sodium pool, and the other was the sodium pool itself and the heat transfer within it. So as part of this work, we looked at new models being developed to model these aerosol dynamics and convection, validated them against 2T axisymmetric data and the 3D experimental data from Manchester. And this has resulted in advances in aerosol modelling and radiation modelling. Looking at the lower plenum, we looked at the heat transfer in the lower plenum itself and how you can improve modelling of liquid metal flows and liquid metal heat transfer. This was done against the escape prototype reactor, with the intention of improving our UK understanding and knowledge of sodium, and hopefully leveraging our experience and data to get more involved in these international programmes. That's hopefully given you a bit of an idea of what we've done under phase one. As I've highlighted, a specification for the National Nuclear Thermal Hydraulics Facility has been developed and is now being taken forward by UKAA. We've completed and developed a number of research proposals as part of this work, with engagement from the UK nuclear thermal hydraulics community. And finally, we've developed a number of innovative models that are relevant to both SMR and AMR technology to increase UK understanding and improve our capability. If you are interested in learning more about the details of the research, we are organising a one-day dissemination event to go through this in a bit more detail, which will take place in Sheffield on Monday the 18th of February. So please let me know if you need more details. That's it from me, and I think the next step is questions for both myself and Ahmed.
So thanks for those two presentations. So we now have chance for Q&A. I'm going to try and make my way to the back of the room. This could be good. So can I ask Ahmed to join Richard at front? And to start with, I'll go to Chris and see. I think there are a number of questions from our webinar audience. So if we start with you, Chris, and I'll come and find a microphone.
Okay, thanks, Ray. Got 3 questions. One from JJ, and the question there was, can the BEIS funding be used for hydrogen fuel systems? I suspect the answer is no. Or nuclear management cloud software systems?
I'm not sure that's a question for either of us.
That's none of you guys, no.
I'll take that one. No.
Okay.
Possibly.
Possibly. We'll skirt around that one then. And the nuclear digital environment has university partners. Are they open to collaboration, and how would somebody access them?
Absolutely are open to collaboration. And that's essentially...
Sorry, Ahmed, can you speak into the microphone, please? Thank you.
We absolutely encourage collaboration. And as to how you access it, we are open, and we have a website, obviously, via which you can leave feedback and questions. We have dissemination events, and we have our contact details here. We've got a Wood PM, so anyone wants to be involved, obviously can contact myself, Mark, or Kathy, who's there, and we can leave those details for you.
Yeah, just to say that obviously as part of the information and links after the event, we'll be sending out the delegate list with contact details for those of you. Obviously you're happy to share, so all the details will be there.
Okay. One from Russ Bully at Vertiv. They're interested in infrastructure supporting the reactor's cooling and specifically electrical systems, including specialised electrical systems and the modelling thereof. Didn't notice how they would be addressed and who and where's the best point of contact for supporting electrical systems.
If I understand the question correctly, it's electrical design and how that might be integrated into the digital reactor design. Was that the question?
I think so. It's around the broader electrical systems and specialised electrical systems that part of the supporting infrastructure is the question, yeah.
All of the aspects of reactor design, electrical, mechanical, civil, others, they are on our roadmap. Certainly, there are all of the aspects that are needed for reactor design will be, although we haven't actually looked at that yet, but they will be looked at in the coming phases. But that's something, are you able to say more on that, Mark? Okay. We haven't actually addressed those or looked at those yet, but it was only a proof of concept, phase 1. I guess it's next phase that will start to address those detailed questions.
Okay, thanks. And a question from a cryptic address, Golf Alpha Romeo. There are many TH models that exist in the international forum, but we didn't see any of them in the presentation. Have they been included in the review?
Yes, we've looked at all aspects of the current modelling, so that includes system codes such as RELAP and Qatar, sub-channel codes like Viper, and also CFD modelling and things like the Castle programme and the research that's being done around the world. So we've done our best to review what's been done there. The initial model development has been done in a number of CFD codes, including Code Saturn and Fluent and other codes. So it is relatively code agnostic in terms of development.
Thank you.
That's it, Chris. Okay, well, plenty of time for questions, so we can open it to the delegates in the room. If you have a question, please raise your hand and also state your name, affiliation, and your question, please. There's bound to be some burning questions. No one? Well, we are going to have an early break. Excellent. Oh, there's bound to be a question right at the back by the time I make my way down here.
done in the spirit of helping you out with questions. I'm John Stam, Technical Director of Wood Consultants in Defence. It's a question for Fraser Nash, please. I wonder if you could comment on the extent to which you think ONR are bought in to the acceptability of modelling purely by CFD and the like, particularly for smooth particle hydrodynamics, but more generally as well.
So we have involved the ONR in the modelling workshop and as much as we can throughout the programme. With regard to smooth particle hydrodynamics in particular, I have to say I'm not sure what their thoughts are on that without a lot more research. But in terms of CFD and high fidelity modelling in particular, they did present a paper recently on their thoughts around high fidelity modelling and LES simulation. And I think they are open to it as long as it's properly used and the uncertainties associated with it are quantified.
Thanks, Richard. Any more questions?
Chris Robinson from MMI Thornton Tomasetti. It might be outside the scope of the work you've done, and sort of addressing this to Richard, but I'm wondering about the location of the test facility in Bangor. Now, you know, obviously you understand the reasoning for regional development and for Wilfer, although, you know, that's in doubt, having heard the news this morning. I wondered if you could just cast any more light on that location.
We have specifically not done an assessment of other sites in the UK as part of this project. The one in Bangor is the one that's preferred, and part of the funding on the Phase 1 programme did come from the Welsh Government. And obviously, as you say, a lot of it's to do with the regional development side and the location next to Wilfer. So the answer is no, we haven't looked at other sites particularly yet.
Sorry.
Bruno Merck, University of Liverpool. Ahmed and Mark, you have shown that you would be highly willing to have any kind of new code development integrating into the digital environment. Do you intend to give any recommendation on the demand for the code development at the end of Phase 1?
Oh, yeah, you can.
I think what we would like to do is move to a point where we can actually identify the need for code development by improving, by looking at where there's gaps in existing codes and actually then identifying the need for actually developing new codes. And that would be very much linked into what I was saying in the presentation regarding to linking with other programs. So where we do identify deficiencies in existing UK codes in particular, we should be looking to target those programs and encouraging them to actually start developing new, more suitable, more capable methods to actually fill in some of the gaps. I mean, we do realise is that many of the UK standard codes were developed many years ago, and so there's both the question of also of the technical the quality obviously for the time was very good, but of course we've also got to think about the development of new skills within the UK nuclear industry, and that will have to feed into code development as well.
No.
Cheers. Hi, I'm Adam Bond from the Nuclear AMRC. Just a quick question on the Indy project. I think I missed this during the presentation. I don't think you covered it, but what you're saying is by 2021 you want to have your sort of kind of first platform being able to launch of the kind of the digital environment. And I'm wondering if you could say who your likely kind of test partner would be of that launch, the kind of customer, the technology. Have you got someone actually in mind already, or is it sort of a bit open at the moment, depending on who you go for the next phase?
Still very much under discussion. In terms of the real-life test, if you like, for the framework, we have EDF Energy as one of our core partners, looking at the graphite damage work. We're also looking to support SMR, AMR program, and also the thermal hydraulics facility. and also discussing fusion. And again, I can't give any more details, but these are a few of the programs we hope that will benefit at the end of 2 years of phase 2.
Thank you. Any more?
I hope I'm allowed a second question. This is for all the presenters. Phase 1 was 100% funded by BEIS, and I guess the next phase is going to be the same. So I'm wondering what your various opinions are about whether it will require, whether you think there's a need for BEIS funding beyond that, or whether it can be totally industry funded. And if so, where's the funding going to come from?
Thank you very much. I mean, this is something from respect to the Indy Digital Reactor Programme. I think this is something that we're still very much identifying. There is certainly a strong case to have a component of this as early as possible, which is coming from industry. Because what we want from a programme like what we're developing is to have as early as possible industry engagement. A key part of this technology has to be developed in close collaboration with the end users. It can't be something which is basically developed in the background, and in 10 years' time we produce a wonderful product which everyone then will come flocking to. That sort of development just doesn't work in software space these days. So we need to have very much early engagement, and that does demand and expect a degree of early industrial engagement within the programme, and that's something which we hopefully that will be built on in phase 2 by whichever model we determine is appropriate for that particular type of technology, and has to have a robust business case around that to encourage that industrial investment, but also continue that investment from government as well, because there has to be a partnership, not least with respect to the UK research base as well, from academia and also national labs as well. So we have to see the new ideas coming through as well, because any technology we develop today in digital space is going to be totally obsolete in 10 years' time. So we need to think about how we bring in forward the continuously bring forward new technologies into the platform.
Okay. Any more from Chris?
Well, I'll give you the other side. I mean, I certainly agree with Mark in that, yeah, the industry's got to be more involved in phase 2, and it's got to be brought along and being used in real projects. I think whether confidently say whether there needs to be more funding is hard to tell at this stage, but I certainly think there should be more industry engagement, more industry funding going forward. And it will depend a lot on where the AMR designs progress.
Okay. Thanks, Richard. Okay. So if there's no more questions, I suggest we break for an early coffee. It's going to take us about 15 minutes to get out the room anyway. So, so please leave. The
technical scope, for reasons I understand, is potentially variable. So I think it's difficult for you to do a level pound-for-pound valuation when you can get different proposals that are larger or smaller in technical scope. So my suggestion to you is that you might interpret it as best value for money.
Value for money is a term that our procurement people do not like to use. The price breakdown in the ITT with the 5% for cost is a disguised value for money criteria. Okay.
I think it says something along the lines of justify how you are going to optimise the outcomes whilst minimising the cost, which was a definition of value for money, but we can't say value for money.
Excellent. Any more questions? No? Okay. Thanks, Si. Thanks, David. Yeah, we're rattling along here. So, okay. So I think next up is Emma. I'll try and find your slides.
my family again. Yeah, you've got an hour now.
Got an hour. You're worried about being too short.
Let's just look down.
Perfect.
Okay.
Thank you.
Thanks very much.
So, ready for an hour on fuels then? And I was worried that I was back up against the lunchtime and everyone would be running out the room. So, yeah, they locked the doors. So I'm going to do a review of the Advanced Fuel and Recycle Nuclear Innovation Programme that NNL have been leading on. I'm a project manager in NNL, looking after these two programmes. So I thought it was worth just revisiting the vision for the fuel programmes that was outlined in the NIRAB recommendation report. And there's a real focus on the commercialisation and industrialisation of fuel. So it's away from the fundamental research, away from the fundamental fuels. It's more towards that. How do we get these fuels through that inevitable valley of death in the TRL levels, to start to bring them to market, with the outcomes being a benefit to the UK economy, a security of supply in some cases, and sustaining the key skills and capabilities to support regulatory and industrialisation of the fuels programmes. So, as I say, the vision for the fuel programme is developing that strong R&D base that will attract the international investment required, support the retention of the inevitably ageing fuel manufacturing capability, including us all, and subsequently deliver nuclear fuels to the domestic and international markets. Again, revisiting the original swim lane diagrams, it's clear that there's a number of fuel opportunities out there, both near and long term. In the short term, supporting the LWR programme through accident-tolerant fuels, and then moving towards more future fuels, so coated particle fuels and PLUTE fuels for future fuel generation. The overall aim of the 5-year programme is really to put in place the skills, the capabilities and the facilities to be able to support test fuel programmes to support the longer term ambition of the UK programme. There's also, as well as the fuel programmes themselves, a couple of supporting tasks, one in reactor physics that supports the ability to manufacture, model and test, well, modelling the fuels that you are planning to manufacture, and as well as the nuclear data programme, which supports the information supporting those programmes. The programme on fuels has been led by NNL, but has a breadth of supporting collaborators across the industry. So it includes a number of key academic institutions, national labs, and industry itself. In support of that, there's also a number of supporting international industrial collaborators who may be seen as end users of the types of fuels being used. So, picking up first on accident-tolerant fuel, and this is one of the major topics in the first phase. Accident-tolerant fuel has really come out of Fukushima and generation of a more accident-tolerant fuel, mainly around the ability to withstand higher temperatures and not to produce hydrogen, and it basically prevents a similar accident. And globally, the industry is looking at a range of options for development of these accident-tolerant fuels, from evolutionary step changes, so iterative from the existing fuels, based around changing in cladding. So looking at how do they improve the coated claddings and what can they put on existing fuel type rods, and then more towards moving towards the revolutionary and real innovative step changes in both fuel and cladding design. So higher density fuel, looking at uranium silicide and uranium nitride type fuels, which have greater economic benefit from being more dense, but also more accident tolerance through having a higher ability to deal with improved thermal properties. And then moving towards the far right-hand side for silicon carbide composites, again, an innovative type approach to an entirely new product for fuel, not necessarily for industry itself, but starting to employ a different type of material in the nuclear industry. And with those come increasing safety and economic benefits through the stepwise programme. So the accident tolerant fuel programme that we've been looking at mirrors a number of the different options. Looking first at the fuel manufacture process itself. Much of the work in this phase has looked at developing a flow sheet and proving the principles of being able to manufacture uranium silicide fuel. It looks like a complicated diagram, but effectively the top line demonstrates the fewest numbers of steps to get to manufactured fuel itself. It takes a lot of the characteristics of existing fuel programs, so a baseline material of uranium hexafluoride, which is similar to the current program itself, manufacture of powder, and the crushing and milling, pressing of a typical fuel program. The major part of the work that NNL have been undertaking in this part of the program has been to try and underpin this process, whilst looking at some of the fallback options, which are less favourable due to increased number of steps, potential for scalability, and availability of the baseline materials. Moving into the cladding work that we've been doing, looking at some of the nearer term options, so that coated, chromium coated cladding options. Work has been undertaken with both University of Manchester and Manchester Metropolitan University to start to look at the ability to reproduce consistent coatings and to look at the scalability of the process itself. So a state-of-the-art review was undertaken to determine what might be the best process for coating of claddings, which was identified as magnetron splttering. And then some testing has been undertaken, both to determine whether the process itself is, let's say, reproducible and a consistent cladding can be achieved. And also, can the coatings be undertaken, or coating undertaken in the type of geometry that would be expected of a cladding tube. So some preliminary results to date have shown that the coating can be achieved and that circular geometries can be coated. And future phases would start to look at optimization as well as irradiation testing and scale up of this type of operation. Looking at the far end of the technology spectrum, silicon carbide composites is a new material, but has shown a number of favourable characteristics, particularly for use in accident tolerant fuel due to its ability to withstand higher temperatures and not having a lot of hydrogen inside it as well. So the work that we've been doing with the University of Manchester has been to develop manufacturing technologies and capabilities, looking at different options for how the composites can be manufactured, with some ion irradiation testing planned towards the end of the programme at DCF. And the other part of that would be the inevitable necessary evil of joining the composites, which is obviously part of the manufacturing processes for end caps, etc., as part of a cladding type material. Again, state-of-the-art review has been undertaken, and to technologies based around lasers, which have small heat affected zones and don't require a additional material to be involved as part of the joining has been undertaken, and some of the initial trials have been favourable. And again, future work would be looking at optimizing and developing that and doing irradiation testing of the types of materials and the joining parameters. So this, as part of the output of phase 1, is putting together a plan for future phases. And I think it's key really as part of the plan is to understand that we're not going for a perfect result, we're going for a workable option. So it's taking forward a few of the options that we've spoken about, building on the capabilities that we've worked up in phase 1, would be looking towards irradiation testing, optimization, and that all-important scale-up, because with the greatest process in the world, if it's not scalable, then it's not going to be economical, and so therefore that's where this process would, or all process would fall over, in fact. So future phases would start to look at the scale-up of the process for the high-density fuel, for manufacturing of the cladding, and starting to look at irradiation testing. So just a quick skip through coated particle fuel. And so coated particle fuels are really suited to high temperature gas reactors, which are thought to be the next phase of, or the nearest to market for the advanced reactor systems. In the UK, we don't really have an industrial capability in coated particle fuels. So this is really the first stage in developing an R&D capability to support that industrialisation. The first phase has, so coated particle fuels, if you imagine a Malteser, it's effectively a fuel kernel made of the honeycomb centre, and a number of coatings on the outside, so Malteser plus. The first phase has been looking at how do we manufacture the kernel, so in installation of non-active equipment to start to look at and generate non-active kernels, whilst looking at the optimization of the coating process through inactive and active testing, which is undertaken by University of Manchester. Looking at a future programme, at the minute, it's in non-active installation through to active commissioning would be a programme in parallel with the coating technologies, coming together in the future to have a joined up coated kernels, which would then be required to be compacted, which would be the third stage of manufacture of coated particle fuels. So moving to the back end of the fuel cycle, which I'm sure they'll be pleased to be known as the back end, but effectively again revisiting the vision for this. And I think this is where for Recycle it's a unique opportunity for the UK. The UK has been reprocessing for many years. And with the closure of Thorpe and the dissipation of that capability, along with the need to support future technologies options, including closing the fuel cycle, the UK has got a unique opportunity to place itself front and centre in the international community. With that, the vision really was around sustaining the capability to develop and design and commercialise the innovative fuel cycle technologies whilst offering radical improvements from the existing. I mean, if we take into consideration how old the technology is within Thorpe, then there's got to be benefits to and improvements to that, right? And we're talking decades old technology. So the research that's been undertaken is really building on those capabilities to really support future programmes. So just touching on why do we need to keep the recycle options open? Well, we've heard about the opportunities again. AMRs are presenting and SMRs are presenting, as well as future new build large reactors as well. So without keeping the options open, we don't want to foreclose early on any of these options and limiting our future. So why would we want to keep the options open, as I say, is being able to fuel the fast reactors, waste management for a expanded nuclear programme, conserving the uranium resources that we have. Obviously, there's a finite amount of uranium available, and this type of technology maximises that availability. From a UK point of view, it opens up international opportunities, but it also identifies some risks as well, which need to be mitigated through programmes such as this. Again, maintaining skills and development. The next phase of reprocessing and recycling could be several decades on. We need to maintain the skills and the capabilities, and as well as the facilities through that time period. So visiting the age-old swim lanes again. So for recycle, in phase one, it was very much around the aqueous recycle. So concentrating on the near-term light water reactors and improving and optimising that process. Moving forward into the phase two, it opens up much wider for the advanced modular reactor opportunities and other fast reactor, all the Gen 4 opportunities. So phase one has been around aqueous, but one of the things to look, the plan would be for future programmes would be to open that up to cover the other opportunities. So as I say, on the current phase, we've focused on the light water reactor oxide fuels reprocessing and introducing some of the new future fuels, such as accident tolerant fuels, starting to pick up that for a reprocessing. Development of an advanced aqueous process, so the baselining of flow sheets for a new optimised process and associated technology and engineering to support that, whilst maintaining the skills and knowledge transfer with recommendations for the forward programme. Again, whilst NNL have led this, they couldn't have done this without the support of, in particular, University of Lancaster, University of Leeds and University of Manchester, who have been key in the roles that have been undertaken. So I know you can't see this at the back because I've been sat at the back, but obviously the slides are available. On the left-hand side, this is a schematic of the current Thorpe PureX process, so the reprocessing. On the right is the simpler, more compact, advanced PureX process planned. And much of the work that has been undertaken in this phase two has been looking at underpinning this advanced process. It brings with it a number of advantages. It has greater flexibility. It's able to deal with different waste loadings. It's not as prescriptive as the existing technology is. Importantly, it's more proliferation resistant. On the left-hand side, the flow sheeting itself demonstrates a splitting out of uranium and plutonium. That is not the case for the advanced process, so therefore maintains a mixed flow through the system, thereby making it more proliferation resistant. It's a smaller size and less waste is generated, which will reduce the overall footprint and obviously the operating and running and maintenance costs. It'll increase the simplicity of the process and, as such, enhance the process safety. So, in support of the clever science that's been done as part of the flow sheeting, there's been a number of works done in the technology and engineering elements to support the scalability. And one of these has been the implementation of a testbed facility into Leeds, the University of Leeds. And this starts to test some of the capability of the key components within the flow sheeting process. So, for example, centrifugal activity and can you scale that up? Is this an industrial or a commercialisation option? And tying into that, a SimPlant model has been developed to start to look at the impacts of R&D, start to assess the preliminary the waste arisings as part of the process, and look at the economics behind the process itself. Really kind of bringing that flow sheet to life in terms of a industrial operating plant. And finally, really, in terms of the work that has been done, it's generated and supported existing facilities and capabilities in the likes of the Central Lab at National Nuclear Lab and Dalton Cumbrian facility, but it's also started to generate engineering scales and lab-based technologies outside of the existing one, so generation of an engineering scale, as I say, at Leeds, uranium active labs at Lancaster, that are really helpful and supportive of not only maintaining the skills and developing the next phase, but really building that skills pipeline and the facility capability. And that's it.
Thanks, Annette. We do have time for questions. I don't expect, again, any from our webinar, Chris, but have you got any there for us? Because they've not seen the slides again.
Where's the slides?
Well, there's one question for BEIS colleagues, I think this one would be. And it's, having heard about Phase 2 programme, how would you envisage the handover will operate between Phase 1 incumbents and Phase 2 suppliers?
Is that in terms of the fuel cycle program, or are we talking, do we know about the things we'll be talking about this morning?
It came in during this, so I think in both elements of Phase 2, but I think principally it was looking at the Advanced Reactor Design.
Okay. So in an ideal world, we would have finished Phase 1 before we procured Phase 2. And I think we all accept that that would be a great way of going forward. Given the constraints that we have on the time set by Treasury to use this budget and to give people maximum time to do Phase 2, we're not in an ideal world. So today is very much part of that handover between Phase 1 and Phase 2. So the way we see it, the Phase 1 organisations have presented to you and are continuing to present to you throughout today their early findings. That should help organisations prepare their proposals for Phase 2, and it means that the incumbent is not automatically the person going straight through to Phase 2. The first deliverable of both the Advanced Reactor Design, both lots, is very much about that handover. So it is to review the outputs from Phase 1 and to consider how they will go forward to Phase 2. Now, if part of your proposal is to talk to the Phase 1 incumbents, which we hope it is, we'd expect that to be in the proposal itself. So how you're going to engage with the Phase 1 incumbent, how you are then going to work with them, including having to pay them if necessary, to be able to set yourself up for Phase 2. So I think that's pretty much how we see that handover. Today is the start of that. There's a chance for you all to go out and have coffee later and talk to each other, but we expect to see that in your proposal for the first deliverable.
Thanks, Si. Any questions for Emma? No, actually very comprehensive and succinct.
I think as Si said, just as Si said earlier as well, was that the open invitation to, if anyone wants to kind of be involved in Phase 2, to just come along and talk. And no.
Hi, Emma.
I hung around too long. I did not sprint.
Ronenberg, University of Liverpool, and then a Royal Academy chair, so halfway insider. Very short question on the Phase 2. You mentioned that it should cover all Gen 4 topics. Will there be some work which will be molten salt reactor specific, so there is imaginable that you could do a completely different kind of reprocessing to what we know today?
So I think the intention is that the phase 2, and as I say, I think I alluded to, there's some discussion going on to sole source that to NNL. I think as part of that, there's looking at because the landscape has changed from when the original swim lanes were put in, and it's starting to look at those other options. In particular in light of AMR competitions and also entry for the UK back into Gen 4 forum. So there's a number of elements I think that would start to look and to just reassess that scope of work. But certainly I think the intention is to make the second phase as flexible as possible to incorporate anything that comes through.
Okay, thank you. Any more? If not, we can break early for lunch. Yeah. So, thanks, Emma. So we can. It's nearly 12:30. I've been reliably informed that food will be ready, even though we're breaking a bit early. Just a reminder that your lunch will be served at the level below us on level 1. We were due to start back again at 2 p.m. I'd like to suggest that we start back at 1:45, 1:45. Reminder to our people, our audience joining the webcast, that there will be slides for you to look at. Hurrah! So have a look forward to that and have some questions ready. So back in the room, please, ready to start promptly at 1:45. Thank you very much.
So the initial report looking at the gaps is delivered. It's being refined as we get more information in, so it's not necessarily an endpoint. We're getting more information still now. And we've also looked at where the UK currently is in terms of its involvement. And I think the essence of that is we have actually very little involvement currently in the design codes, unfortunately. So the final report is due in a couple of months' time, and that's trying to refine how we address those gaps in the codes and where the UK might actually be a significant player in that. So for SMR, so like water reactor technologies and for Gen 4 specific activities. We've been prioritising those gaps and how we might attack them and developing a roadmap to produce that research plan. And essentially this says that in a little more detail. This slide and the graphic at the bottom just tries to pull that roadmap together. So where is it in the SMR Gen 4 space are the problems? We know what some of those are. And the BEIS theme work obviously feeds into that activity of sorting out those problems and trying to address those gaps. You have the ONR, the UK specific activity, the GDA, the General Design Assessment there, and the international code bodies that we're looking to influence. And one of the thoughts is that it may be that we'd be better off with a UK working group that addresses these design codes and standards as a UK-wide activity rather than expecting each company to send people to these events. Certainly populating the sort of 20-odd committees in ASME can be quite expensive for companies. There are other activities here, things like the university link. So the work for EPSERC and TAGSI and the Horizon 2020 type activities, maybe not directly related, but have got underpinning information that's been generated there that can then feed into some of this work. So, very briefly, I say I apologise, this is just very much a flavour of what's going on, but there's been a big study of what the issues are, trying to involve and engage all the reactor vendors and developers that are available at the moment, trying to take a collaborative approach to all of this. And even now, we would still welcome input into this sort of activity. If people haven't been talking with Wood, then please do feel that you can do that. And actually, as we said at the beginning, this work supports the other materials and manufacturing activities as well in these themes. The UK may have key areas of expertise that it can help fill this gap. Thank you. Yeah, if that's okay. Okay, so the next one, so that was theme 5, so we've gone from the end right back to the beginning. Now on the structural materials activity in theme 1. This is the materials and manufacturing technology evaluation. And this is an activity that we're doing with TWI, Nuclear MRC and Manchester. And I'll make sure that they're well recognised here. In terms of the way we've addressed this, we've attempted to recognise what the manufacturing technologies that are out there at the moment. We've gone through the likes of Nuclear MRC, the Advanced Forming Centre in South Clyde, TWI, to get what those technologies they see as being available and potentially relevant to try and get down the capital cost of reactors. And having got that information, we've gone around, again, a whole range of reactor vendors, 6 or 7, and trying to find out from them what they felt the industrial pull was for these manufacturing technologies. And out of that activity, so right from the beginning, we've tried to build in the exploitation as part of the program. And from that activity, 4 technologies, 2 around welding, 2 around near-net shape forming, came out: electron beam welding, particularly local vacuum, transition joints. So those joints between different materials, always a problem in plant. Palametallurgy and isotopic pressing and additive manufacturing, a little bit about each of those. TWI and Nuclear MRC are essentially doing most of the processing for this activity. And Manchester's key role is in actually providing the real leading edge process modelling around the EB welding, where there's opportunities there for reducing the amount of experimental work that's required. We're also doing a lot of the mechanical evaluation. Again, that's one of the key issues. These manufacturing technologies come through, but actually having the underpinning data to make them viable and understood for use in plant is costly and difficult and time consuming. And that's where I think we can hopefully make a contribution. We're also reviewing some of the materials activities potentially for the future. A lot of information on here, and I recognise you probably won't read it at the back, and I won't say everything that's on the slides. Just trying to highlight a few things. From the electron beam welding, some of the benefits of that, particularly the local vacuum system that TDI have developed in the past, essentially eliminates the need for a large vacuum chamber, reduces the capital cost, and means that you can widen the range of applications that you can use this for. EV welding generally has the attraction of being able to provide very thick section welds in a single pass. So going from sort of months of welding for large pressure vessels down to hours potentially. So capital cost and time shortening, there are huge potential benefits there. In terms of applications, everything from primary pressure vessels all the way down to all your sort of joints and things in plant are possible. What we've been trying to do is compare the E-beam welding techniques. We talked about this local vacuum. That means you don't need a chamber, but we're trying to compare that, where the vacuum's less, with conventional high vacuum chamber welding, and also different materials as well. So, in terms of our project at the moment, all the welds are produced, Nuclear MRC and TBI have delivered all those on time, and we're in the midst of heat treating some of the materials. We've looked at a low alloy steel, or two low alloy steels in actual fact, and an austenitic stainless, trying to bridge the light water reactor technologies and the Gen 4 technologies as well, again to try and meet the BEIS requirements there. Here, this is one of the biggest activities we've got on in this programme, and we've got a whole range of evaluation work going on, from fracture toughness on the low alloy steels, stress corrosion cracking initiation in light water reactor chemistries, molten salt corrosion is a key one as well, and potentially mechanical testing in liquid metal environments as well. So there's a whole range of activities here, and it's here where Manchester are key in doing their process modelling, particularly the SA508 material. And the key issue here is that actually it's a really complicated material to model, and to get right and get useful information out of the modelling requires a lot of understanding of the microscopy, of the metallurgy, and the phase changes that occur. And this is where I think Manchester have a real lead in this country. I put in a couple of ideas around ERC work for phase 2. I won't dwell on those. If there's interest, you can talk to me later, but potentially vessel component demonstration are things there that could be looked at. Transition joints. Here, we're looking specifically at joints between, again, low alloy steel and austenitic stainless steel. So it could be applicable to light water reactor, but also some of the Gen 4 systems as well, where you have controlled temperature on vessels and things like that. The idea here is to try and eliminate some of that multi-alloy welding that causes so much problems in plant currently. So you end up with a simpler thing where you have to, yes, produce two welds, but they're both of the same material. So it's relatively straightforward. Nuclear MRC and TBI have been very active in this, and they've produced the materials by two different routes. One a weld and forge route, the transforge activity of TBI, and the other by a powder met hip activity at Sheffield in the Nuclear MRC. Here, we're doing mechanical testing and mechanical evaluation of that work, just to try and progress that. This activity and this technology is probably one that requires more optimization and more development of the actual manufacturing, whereas some of the others are more well developed. Panometallurgy, hipping, veneer net shape. Again, a lot of benefit in terms of potentially chemical homogeneity and reduced scattering mechanical properties. Yes, you can end up with near net shape. So it's similar to a casting, but you can hopefully get forging type properties from that, and that's one of the things we're looking at here. In terms of the components, you might be looking at pressure vessel components, pump bodies, some of the smaller type components, non-critical components may be targeted by this sort of technology. Mainly, we're looking here at comparing the Panama hip with the wrought performance to see whether actually you can use this thing as a means of getting sort of cast type components with forged properties, all the benefits there of reduced material usage and things like that. So we're doing fatigue work, for example. There's a little graph at the bottom here that shows some of the fatigue data we get in, which suggests it is as good as forged material, which is encouraging in terms of fatigue at least. And we're generating other materials as well. Additive manufacturing, in some ways, one of those buzzwords in the research world at the moment for manufacturing, but potentially, again, offers some benefits in terms of near-net shape and complex geometries. Interesting with this one, opportunities for local repair as well of components. That might be an area where it could be particularly beneficial. And also, similar to the parametric hipping, you could envisage actually incorporating different materials into a component. So, you know, if you wanted a hard-facing seat for a valve, for example, you could include that in the one single manufacturing operation rather than having to attach it subsequently and things like that. I'm saying that probably applies for the parametric hip as well. Here we're trying to assess the effect of the deposition on the mechanical performance, particularly in respect to the surface finish, and that comparing again with wrought properties here. This has all been produced by TWI. They've done a really nice job producing some samples for us, and we're in the midst of producing tensile and fatigue samples at the moment. Again, a number of things that you could look at there in terms of, again, improving the deposition conditions to give you a better surface finish and things like that to help you in the future. That's just a very quick run-through of this programme, and there's an awful lot going on in this. We've been really fortunate in having a really strong team delivering this, so actually we're in pretty much where we'd hoped to be by this stage of the programme. I think we've got to go through till August this year. Thank you.
Have we any questions? Because we can, as we go through, I realise that there's no time for Q&A at the end of this whole session. So if there's any quick questions for Andrew, otherwise we can move on. You got away with it. Okay, excellent. Thanks, Andrew. So next we have Hugh Dawson, UKAA.
Right, good afternoon. I'm Hugh Dawson. I'm a material engineer from UKAEA, and I'm the project manager for the project Nanostructured Steels to Extend Operational Performance for Nuclear Reactors. The project was awarded under the SBRI competition for Advanced Manufacturing and Materials, and it is a University of Sheffield project, but with subcontractors UKAEA, NNL, MPI, and Sheffield Forge Masters. So the project sits here in the BEIS Nuclear Innovation Programme, the structural materials and manufacture. We are in phase 1, which started in January 2017 with a technical feasibility report, which was concluded in August 2017, and then we were awarded the contract in December 2017. And we've now moved into phase 2, which is the implementation of the project, which officially started in January 2018 and will be concluded at the end of August this year. So the aim of the project is to develop a realizable, high-value nanostructured steel that can extend operational limits of nuclear reactors and also help grow the UK manufacturers' market share in the global nuclear market chain, which is predicted to grow for the coming decades. So we'd like to be able to extend the operational lifetime of nuclear reactors, but also future generation reactors, such as Gen 4, are going to be operating at higher temperatures and in more aggressive, corrosive and radiation environments. And quite simply, most of the current grade alloys that we use won't be able to survive in this environment. So these reactors might not be realizable until we can develop a new, improved generation of alloys. One way of meeting the demanding material properties that are required for these nuclear reactors are using nanostructured steels. which in this context is including a fine dispersion of small nano-sized particles. These are extremely good for nuclear reactors as they contribute to high temperature strength and creep resistance by inhibiting dislocation motion. The particles act as recombination sites for radiation-induced defects, and particles can also trap gases like helium and hydrogen, which can reduce swelling and embrittlement during operation. But there's no point being able to produce new impressive alloys just in the lab. We need to be able to produce them on an industrial scale. So there are currently two main ways of producing nanostructured steels. One is the more standard way of having the particles precipitate out during production and processing, and the other is through powder metallurgy routes. And powder metallurgy routes have produced some impressive microstructures and material properties, but they are very expensive to produce and very difficult to produce on a large scale. And there's currently nowhere in the world that you can produce extremely large components using these methods. So it's unlikely that this route will be able to produce large-scale components anytime soon. So we're going with the precipitation method, and we're trying to maximize our nano dispersion using a combination of careful microalloying selection, optimizing the thermomechanical processing routes, and a particular feature of this project is that we're going to try and use a high nitrogen content in the steel, which is quite difficult because it has a very low solubility. But if we can keep a lot of the nitrogen in there, then we can hope to precipitate out a lot of stable nitride particles. And also we want to be able to upscale this production so that we can get the same properties out of a small batch as we would from a large batch as well. So the project didn't have the best start due to personnel issues at the University of Sheffield, which led to UK AEA taking over the project quite recently. We've now rescoped and redesigned the project, and it was formally restarted in November of last year. But we are still sticking on the same time frame, which means we still aim to finish in August this year. So as I said, UKAA are now managing the project, but we'll also be leading the microstructure and mechanical testing. NNL will be leading the compositional measurements and the corrosion testing. MPI have led the modeling of the alloy chemistry, and they are currently producing the alloys for us now, at which point they will be transferred over to the University of Sheffield, who will do the thermomechanical processing there. Sheffield Forge Masters are doing some testing for us towards the end of the project, but they're also overseeing the business case for us and acting as the critical assessor of the technology. So the feasibility study has been completed, and we are now in the production and analysis phase. So MPI are currently casting 5 different alloys, which are all based around the P91 composition, which is a fairly well-known nuclear-grade alloy, but we'll be playing around with the composition a little bit, particularly exploring high nitrogen contents. After this, it will be gone to the University of Sheffield for thermomechanical processing, and then we will begin our testing phase, which we basically want to find out indicative properties of the materials to see if they have promise in a nuclear reactor, so their thermal stability, their tensile strength, their corrosion resistance. And this will take us up to about May of this year, at which point we'll be able to give a preliminary report with information on the castings and on the material properties. But we'll also use this report to choose the most promising alloy out of the 5, and this will be then brought forward to a larger casting, which will be 200 kilograms, and then we'll move on to further testing. So some of these tests will be different, but a lot of it is just to see, have we kept the same material properties when we're going up to a bigger cast. And that will take us to the end of the project in August 2019, where we'll have a full report and hopefully some interesting data and some a promising new alloy. But the whole project is designed as part of a wider 5-year project, so we hope we can take that forward beyond August. At what point we'll be able to do more detailed material investigations and keep moving up the scale of casting that we can do, hopefully to a full-size industrial batch. So here's a Gantt chart of the project. If you can read it, it might be able to tell you some of the particular testing that we have planned, but also the timescales that we plan to act over. It's a fairly busy project because we still need most of the same results as we needed originally, but we have a shorter time frame. But we're still confident we can get all the information we need and still finish on time. So yeah, so I'll leave it there. Thank you.
Okay, any questions for Hugh before we let him escape? Or at the back?
Yes.
Sorry, just to repeat for the webcast, in case, is there any welding envisaged in the later stages of the programme?
Yes, so originally there was meant to be some electron beam welding in this stage of the programme, but there wasn't the time frame, and I think any welding we would have done at this point would have been too simplistic to make any useful decisions. So the next stage will definitely have some welding analysis, which is important for any material, but when you're working with nanoparticles, it's extremely important to understand the welding behaviour. Yeah.
Thanks, Hugh.
Thanks.
Okay, cheers. Okay, next, Andrew Moffat, Fraser-Nash.
Good afternoon. Well, so the swim lane diagram again. The Fraser-Nash project sits within the yellow box, which is the nuclear structural materials. I've been back to the original ITT to try and pick out what the expected outputs were, and I've changed them a little bit to be in line with what we're actually delivering. So it's not as bad as it sounds. So the initial one there is understanding of, well, I've said power beam welding. Originally that was materials and manufacturing processes. We shied away from materials because that's quite reactor dependent. When we thought about the nuclear world and all designs, it's welding which really links them as the key manufacturing technology. So that's why we concentrated on that one. And that's for the wide-scale implementation in future reactors. So we've not narrowed down any particular reactor design. Welding is applicable to all designs as far as I know at the moment. The next output was advanced modelling approaches validated by experimental data. So we are still doing that. It's I suppose in this case, specific to power beam welding rather than all manufacturing processes, but that's an important one. And then a forward 5-year programme, which is what we'll be developing towards the end of the project, although we obviously have ideas about that with the launch of the next phase today. Our work programme for phase 1 really has 3 areas. It's weld residual stress modelling, and understanding, probabilistic methods, and fracture modelling. When you're doing a structural integrity assessment for high integrity components, one of the important inputs is weld residual stresses. If you're using TIG welding or something which has been in reactors for years, then you can go to R5 or R6 or BS7910, whichever standard you want, and you can pick out the bounding profile and you can use that as an input. That's not the case for electron beam or laser beam welding at the moment. You have to either use bounding profiles or do a lot of expensive testing yourself. So really this work is about trying to produce a body of evidence to enhance those assessment codes. The second method, again, probabilistic method, the second work package, probabilistic methods, is an interesting one. Probabilistic methods are used a lot in structural integrity in the operation, or justifying continued operation, but they're not really used in design at the moment. This work, our work package in phase 1, focuses on trying to develop a framework for the application of probabilistic methods and trying to deal with some of the trickier aspects to guide people on how you would do those assessments. And then the third package is fracture modelling. Again, fracture is one of the key inputs into a structural integrity assessment. The programme really is trying to develop that background information around on a fracture of electron beam and laser beam welds, but it's also trying to develop methods around what you do with thinner sections and the effects of constraint, which are sort of a key area of research for those assessment codes at the moment. Our project is a consortium of University of Bristol, who are doing a lot of the work on the fracture modelling, or the fracture testing and modelling, and also on the electron beam weld and laser beam weld modelling. Nuclear MRC, who did the welding for us. Camel Laird, who also did some welding for us and formed part of the probabilistics work package. And Vector, who are a residual stress measurement organisation, one of the leading ones really in the UK. And we've got a number of supporting partners which we consulted in the development of our proposals and as we've been going along throughout. I've got some technical slides now, and there's words and graphs. I won't go into all of them. You can look at them afterwards. But this is the type of thing we're trying to do in the residual stress welding. We develop thermal weld models. We can validate those against thermocouples. And then we're using a number of techniques. We can measure residual stresses. We, at the same time, are developing techniques which are, I guess, simpler perhaps to apply, but still based on a mechanistic understanding. And a lot of the good work that's been done at the University of Manchester as part of the Newman project. So that's one aspect. On the probabilistic methods, there's a number of areas there trying to develop the framework, but also trying to think about probabilistics in weld residual stresses. At the moment, we just use bounding assessments. And if we want to start using probabilistic methods and getting the understanding around them, we need to sort of challenge those assumptions and try and think about distributions for materials inputs, for stresses, for weld residual stresses as a whole. The next, I think the future of probabilistics is important because we have fleets of SMRs. That's an inherently probabilistic problem. Whereas with the current large reactors, you can do deterministic assessments because there's only a few of them. But if you've got 100 or 200 SMRs, it's very much a probabilistic problem. So I think that's an important area of development. And then the fracture modelling. There's a number of areas here. The exploitation of this is hopefully a section to enhance R6 and the treatment of thin sections there or a loss of constraint. But it's also this database of information on fracture in electron and laser beam welds. I've tried to bring together what the programme benefits are. So really what we're after is greater flexibility in design. We want to be able to take the right technique for the right application. So in some cases it might be TIG welding, some cases it might be EB welding, but we want that flexibility. And by generating this body of knowledge, we're effectively reducing the risk around implementing those technologies. At the moment, electron beam welding and laser beam welding, they are used a little bit, but they're not used in a wide-scale way. And that's because that basic understanding isn't at a maturity level that's required. We're enhancing the structural integrity assessment codes to make them fit for the future. Our 5 and our 6 are set for the current fleet, and as we go forward, we need to keep those up to date. And that's about developing this portfolio of evidence. I suppose the key takeaway here is that what we're trying to do is develop UK technology to reduce the cost of nuclear new build. We want to be able to optimise the design and the operation, and that's where this work fits in. On my final slide, what I've tried to do is bring together where I think all the the Nuclear Innovation Programme contractors are working together. So you're going to hear about a whole bunch of projects today, but I think the focus for a lot of them is broadly welding. We're generating understanding for assessment codes and for design codes. I've heard from Andrew already. We're improving speed and quality, and that's what you'll hear through the nuclear MRC talks. And we're looking at the application in modular construction, and that's what we're hearing from Campbell Laird. So those organisations are working together quite nicely and quite collaboratively in a way, which has been a nice aspect of the programme. As we look forward to phase 2, I guess we'll hear more about that in a few minutes, but it must be more applied and we must demonstrate capability. We've got to get closer to deploying this technology. And the final plug here is on the all the advanced manufacturing materials contractors are coming together on Wednesday to present a little bit more detail. So this is the taster, and please come along on Wednesday if you're interested in finding out more about each of the projects. I think that's it. Yep.
Any questions for Andrew, if you're not going to be there on Wednesday? Chris? Yeah, they've obviously been dazzled by the slides, so no questions. Okay, thanks, Andrew. And next we have Carl from Nuclear MRC.
Okay, yeah. Good afternoon, I'm Carl Hitchens from Nuclear MRC, talking about the mechanisation and automation of large-scale manufacture and assembly. So this is 2 projects that we've been working on, one called Simple, one called Inform, both with this common aim, trying to reduce the cost of nuclear reactor manufacturing. I drafted the original concepts for these, and I really must say thank you to all the engineers involved from the various organisations for making some sense out of those original drafts. So apologies to you guys that had to do that. But essentially it's 2 competing concepts. One is process to part and one is part to process. And I'll talk a little bit about that in a second. So with Simple, it's very much about one platform with as many manufacturing processes as possible delivered on that. Imagine it's a bit like Thunderbird 2, the green one. One deployable platform, pick the end effector, pick the module you want to do the piece of work you need to do. This is what it looks like here, where we might have a machining platform with a welding head, NDE head, various applications. Now to develop this interoperability, we need data and communication. So we chose one head in particular for this phase, which was the arc welding head, as can be seen here. And we looked at how many sensors can we put on there: vision, acoustics, phase, monitoring, power consumption. And then how do we understand that data? And this was very much at the heart of the spec of the original concept. A data platform, a data interoperability, where all data could be managed in one format, time-stamped, understood, and then from that collection of sensors, could we make some sense out of what was going on in the manufacturing process? Maybe some soft sensing, where 2 or 3 sensors collectively build a bigger picture than one on their own. Having this data platform here is actually a great opportunity to good links into the digital manufacturing strand of this work. We've got the in-production data. What can we do with that for through life and plant life extension applications? Is the data there we can use? Can we tie it into the front end, where we bring in data from source when it was dug out of the ground, so we've got full manageability of that product life cycle? As we've said, we worked primarily on ARC platforms, but we've kept it flexible. So future phases, we always hoped would do maybe forging, machining, assembly, whichever manufacturing process you were thinking of, all on that common platform. So that was the Simple, been described as anything but simple since we launched it. The other one was Inform, intelligent fixtures optimised for radical manufacturing. I make no apologies for the radical, I needed an R desperately. And I was a teenager in the 80s, so that's how it ended up in there. And this is the opposite. This is processes to the part. The part static, intelligent fixture, understanding its environment, what's going on around it, and then deploying manufacturing processes to that fixture. They hang on there. Which one do we tackle first? We can't do everything. We try to pick the most difficult, or the one we thought we get most benefit from. Local vacuum, electron beam welding. Big chambers, expensive assets. If we can make it deployable, it's going to be more adoptable by industry. That's our thoughts behind it. We talk about thick section welds, good tie-ins in with the interior work done by wood. That could extend that. The primary task here is to create a good vacuum, not good welds initially. That's a much bigger challenge going forward. But there's been a series of concepts developed, and a novel one here which allows beam checking before manufacture. So I'm looking forward to seeing that progress through, and there'll be some demonstrators of that as well. We then have the fixture concept. Again, got radical in there again. Looking at different ways of fixturing a large components for assembly, ease of manufacture. And again, a number of design iterations have been gone through, and we're coming round to the fact that gravity's, you need it on your side. So most of these are vertical build concepts. But then we thought, the thought path led on beyond that. So we've got a fixture, but what about the factory? Normally factories are just a shed that fixtures live in. Can't we make it integral to the manufacturing process? Provides datums, maybe some shielding for heat treatment, electron beam. We left nothing out of the bag. Radical concepts as well down here, circular movements. But what benefits could we get from that by taking fixtures and manufacturing and make it really embedded, or design the factory around that process? With the SMRs and AMRs, we're looking for low volume compared to automotive. Manufacture, things have got to be done slightly differently. We can't have these disparate manufacturing cells. And then disseminate and leverage and exploitation. We're already seeing some of that now. We have a number of projects with our research board, but one I want to mention in particular is the EPRI with Electric Power Research Institute. Nuclear MRC are currently in a programme of developing advanced manufacturing techniques for a 2/3 scale reactor design, just to show the art of the possible. So this is looking at powder bed, blown powder, high accuracy machining, scanner machining, advanced NDT, thick section welds. And the three projects, Inform, Simple and the EPRI, have both been excellent really. We've got fixtures, we've got data, we've got process development. So the three do mesh quite nicely, and we're getting leverage between the three going forward. And then talking about going forward, some of the emerging strands that I'm starting to see here. Future Forge, led by Sheffield Forge Masters. A great opportunity to maybe use some metrology techniques and sensing, just to name a few, to advance forging techniques and make them more profitable. The fixture factory concept, a lot of work needed there to really understand what benefits it could bring to low volume manufacture of reactors and how to do it correctly. Hot NDE, the closer we can bring NDE to the point of validation of weld, the reduction in time there is quite important. That's another good strand that we've seen for ourselves. In-process inspection, again, bringing inspection close to the manufacturing has got to be a benefit for manufacturing optimization. Local vacuum, electron beam welding, that does need to move forward. It's a great technology. It's how we do that and what resources are required to keep maturing that. And then a big topic here is digital twin for nuclear. What does it mean and what benefits could it bring to new build, through life and end of life, and possibly life extension? And I think that's a really big topic that a lot of industry need to get involved in to understand. And then the last one I've added there is environmentally sustainable manufacturing. I think anything we do, we need to think about the environmental sustainability. If it's not, it won't be adopted, and essentially it will be dead research. So I think that's an important topic to keep in mind when we move forward. I'm not sure how I'm doing for time, but the last slide really is about a bit about the Newman community. When I first started Nuclear MRC, we had a Newman programme funded by EPSRC doing fundamental work into materials, welding, portable manufacturing. That community is still ongoing, even though it's not funded. And this is one such event on Wednesday this week. I know it's a short notice, but we will be presenting much more detailed technical information. I say we, the lead engineers. We've got Matt Smart and Ben Cook and Craig in the audience. They'll be presenting some more detailed information about these two programmes. You're very welcome to attend, and I think there'll also be some discussions about the next phases of this this funding call. And like I say, that's on the registration. Please feel free if you want to join us there. Okay. How's that? Thank you.
Fantastic. Thanks, Carl. Thank you, sir. Okay, any questions? Chris?
Yep.
Nope. Any questions for Carl? Oh, you're all going on Wednesday. Okay.
Thank you.
Thank you. Jonathan?
Okay, thank you. Okay, good afternoon, everyone. I'm Jonathan Brown from Camel Led. I'm going to talk about a project called Fit for Modules. The presentation I'm going to cover, we've actually completed our project at the end of April 2018, so we published the results. What I want to do is take you through the process that we went through. So tell you about the actual project and what the aims of the project were and how we went about it. And then I'm going to finish with a roadmap, which was the interventions that we're recommending to take forwards. In terms of the project, and I start here with a bit of background. So it came out from the NIRAB Research Development Programme. And they were looking at a 5-year objective here, which was to produce a suite of modular construction techniques to enable effective nuclear plant build. So the whole theme about this, and particularly around Fit for Modules, was about being able to mitigate risk in schedule and schedule build. So some of the other things we've been talking about today are about actually attacking cost base and doing things cheaper. This project is all about how you bring some of those things together to be able to actually build off-site modular units and be able to take them into nuclear plant and nuclear plant build. So the whole thing here was about maintaining schedule and maintaining your cost predictability. And so on the bottom here then, you can see what we were looking for from this phase 1 was a roadmap of interventions. And these interventions would enable the UK to have the capability through the design phase, through the manufacture, component manufacture, through to assembly, and then into commissioning and transportation. One of the things I'll talk about a bit later on is if you build these things off-site, move them onto site, and then you've got to recommission them and go through all of that again, you've actually lost a lot of the benefit that you've got from doing it off-site in the first place. So how do you maintain that integrity through the transportation so that when you install on site, there is a minimal amount for retest? So in terms of the project and the process we went through, the top line on here was actually the customer reporting, and over the 12 months we had frequent meetings with the customer just to talk about where we were, particularly about aligning this with other projects which were ongoing. There was a project team. Now in the project team, I was already Camel led, we were pleased to lead that, but we had Lang O'Rourke, Arup, Fraser Nash and Westinghouse also helped us with some of their experience of building modules and some of the work that they've been doing on that. And then alongside the project team was an advisory board. Now the reason for the advisory board, and we had all the good and the great on there from a whole series of customers, and we had BEIS and we had others involved in that. But that was really to make sure that we got the alignment at the outset in terms of where the project was going and a bit of sense of direction then about what we wanted the project to achieve. But the important work was the stuff done by the Modular Alliance. And there was something like 60 companies involved in that Modular Alliance, as well as the regulator. And the regulator took a full and a very active part in this whole program, as well as some financiers, And I mentioned multi-sector SMEs, but we had people from the automotive industry, from the shipbuilding, from the oil and gas industry, so it wasn't just a nuclear sector activity. When we were running the workshops as well, we actually looked at 3 key areas. And I'll start at the bottom actually, because at the bottom it was about technologies and techniques. In the middle there was about processes and methods. And the one at the top was about people and culture. And you may not be surprised to know that actually people and culture was probably the area that's most important to address. I'll come back to that at the end. So in terms of a roadmap, this is what it looks like. Now I know I'm going to read through some of this because I know some of you at the back won't be able to see that too well from there, but you'll have the slides to take away. We start on the left-hand side with this concept of matched funding. Now here, actually, this is about organisations putting time and effort and their leadership and their organisations, if you like, committing those organisations to the outcomes of these processes. It's really important that, because when we talk about sort of matched funding, if government are putting some money into it here, actually industry's got to put something in as well. And so alongside these pilot phases, and there are 7 on there that I'll take you through, there is also a module development centre. There is somebody where this activity comes together, where organisations can come together and collaborate. And it's back to this people and this cultural thing, is actually people working together here, bringing their own contributions, but actually working those contributions together to actually achieve the outcomes. There's another thing on here which is qualification centre. So I mentioned earlier about when you've produced these plant and this equipment, you actually need to be able to test that, and that's important to be able to do that with a third party, so you've got an independent verification about what's been undertaken, and that actually regulators can take credit for the fact that you have got third parties involved in being able to give the qualification for this plant and equipment. There's also a thing on here about collaborative learning. And again, there are some new skills. When we talk about digitisation and we talk about digital twin and we talk about some of these other tools and techniques, actually there's a whole process of education around that, right from the leadership through to the actual practitioners and technicians. And we shouldn't forget that actually providing that education, providing that training, and actually being able to deliver that to various cohorts is an important thing for us. So on here then, so you've only got the pilot phases, I'll run through those quickly, and also then there's a scale-up phase when actually you've demonstrated that you can actually conduct these activities, but then can you do that in a meaningful throughput which would actually support a nuclear programme build. And I've showed another piece on here which I've called rollout, because at the moment we don't know how much actual activity is going to come through here. We like to think it's a 16 gig, we like to think it's a much bigger program, but we really don't know. The one thing I will leave you at the end is, this is not about nuclear. Quite frankly, if we can do this, you can apply this to any program. You can apply this to shipbuilding, you can apply this to automotive, you can apply that to whatever technology, fusion. So actually the techniques we're learning here, and I think that's really important, because if we get fixated on a single project, actually, it can become a bit of a dead end if those projects do grind to a halt or if they get delayed. The important thing here is that there's a huge program of work associated with this. But actually the roll-up here could be quite important, is how do you scale that in order to meet future demands? So I said I'll go through these pilot phases. The first one on there is all about structural modules. So this is about heavy modules, maybe 1,000 tons, being able to build a module, being able to actually handle that module itself, to have intelligent fixtures. You've just heard some of that from Carl earlier. And then how you can track that. The next area on here is about process modules. So when you're actually looking at processes and control systems and how do you build and integrate sort of system modules here, and then to be able to certify those and post-transfer verification. So once you've got it to the site, how do you plug it in, and how do you have that self-diagnostics that sort of checks through and tells you that everything is still functioning as it was when you commissioned it. The third one on here is about digitally enabled quality assurance. and I put this in here, but this is about an end-to-end thing. So every organisation that's involved in the build of this is linked to this digitally enabled system here, so that all the quality records are built up as you go through here. What we're not looking to do here is to assemble at the end a big quality record. That is compiled as we go through this process. The fourth one on here is about transportation and moving these modules around and actually being able to have the assets for transit, for receipt, and particularly installation. What we do find is quite often we can build things and we can export them, but can you receive them at the far end, and being able to actually join that up. The fifth one on here is concurrent engineering. I know we all talk about getting to a point of design freeze, but design doesn't freeze. Design continues as you go through manufacturing, as you go through assembly, as you go through installation and commissioning. There are always challenges, there are always questions get put back to the design authority. We need to be able to answer those rapidly and be able to mature that design through the construction, through the installation, through the commissioning, and actually through life, and maintain that design and that design integrity through the life. And the last two, the first one relates to Project 13. And what we're talking about here is the principles of Project 13 about good clienting, about innovation platforms, about some of the principles that they're building in there, I think are really good things for us to actually adopt within our nuclear sector and our nuclear build. So we're actually recommending here that we look at that, and a lot of lessons coming out about delivering high performance infrastructure. And the last one was that thing I talked about was about training, about leadership, about compliance frameworks, about collaborative programs. And a lot of the stuff that we generated here in terms of training requirements have been passed on to the Nuclear Skills Strategy Group. And obviously they're working as part of a nuclear sector deal, but we're asking for them to look at the curriculum and look at the training requirements so that we get something consistent across the industry. So I'll just summarise. I mean, I said earlier about some of the techniques and the tools and stuff, but the three things that I'd like you to sort of take away from this is that actually we've got many of the tools, many of the techniques, many of those things. What we really want here is to demonstrate about how all these parts come together. And actually we've got the sum of the parts, being able to build these off-site modules and supply them for nuclear plant build. I mentioned earlier that this isn't about nuclear, this is about major projects. And whatever we're applying here will apply to major projects in whatever regulation and whatever requirements you're trying to meet. And the final thing is this thing about collaboration. The most important thing, the thing we've most got to get right here is collaboration. And by that, I'm talking about having a shared outcome, but the behaviours and the way that people contribute towards that shared outcome. That, to me, is the most important thing, determinant about the success of this programme. Okay, thank you very much.
Okay, thank you very much, Jonathan. Any questions for Jonathan? Okay, you managed to get away with it. Okay.
Sorry?
No, you're okay. Thanks, Jonathan. Okay. Now towards... so there's more information there from Jonathan, and now we go the final presentation today. So bear with me again. You look at family snaps again. That's the Chagrin family in their natural habitat.
Right, last session of this type of the day before you can actually get back out there, have some coffee and start talking to each other about what we're going to do next. So, this is the bit I've been looking forward to. So, this is the standard swim lanes, but we've kind of brought all the swim lanes together at the end to show what we're doing now. So the first phase of this project, as you've heard from the various people who've been speaking, we set out SBRIs, we set out a number of things we launched back in 2016, 2015, and those projects are coming to the end of their process now. The next bit, this ginormous arrow here, to my knowledge, has been announced about 5 different times in 5 different guises by 5 different ministers. So if you're adding it up, we've got about 100 to 120 million pounds. That is not the case. It's the same 20 million pounds that has been announced over a range of the last 2 years. Most notably, it's in the nuclear sector deal. And it sits alongside an industry commitment to bring around about £12 million into the area. And Richard Harrington announced that this was going to be delivered and launched by the end of last year in November. You'll note it's now past the end of last year. The reason for that is we were stepping up to launch this in December, but we decided to do some industry consultation. So the ETI and Jonathan Wills and Mike Tynan from the chair of the NIRAB went out and spoke to a range of people in the industry about the grant call that we were proposing to launch. They came back in December, and on the back of that feedback, we've adapted the grant call a little within the powers and the remits that we have to do it, to try and take on board a lot of that industry feedback. We can't fix all of the problems. We have a very defined spending period set by the Treasury, so I only have funding up to a certain point in time. And a range of the feedback was that it would be nice if there were some large government announcements that provided other certainty. Well, I can't do that either, but I can give you sufficient time on the bidding process for potentially government to make some large announcements, or not. Who knows? So we're launching this today. The documentation, I'll say this again at the end, should be going live at around about 5 o'clock. And the whole point of this process was to take the money we've invested in phase 1 and now to try and bring it all together in an integrated manner to demonstrate something real, to go out and put a grant fund out there for people to bid in to do something real with the next phase. So, a little bit about the scope. There'll be a lot more detail in the guidance documents that are coming out at 4. But this is sort of a top level. There will be a £20 million fund. This is a grant fund, so it's not a procurement. We'll get to that in a minute. And the main aim of it is to produce a technology demonstrator, or a number of demonstrators, that include advanced manufacturing and construction techniques. We're looking for you to produce something tangible, something real, a thing at the end of it that shows the various techniques that you can bring to bear on modular manufacture and materials can be done in the real world. An awful lot of the speakers before me have spoken about how they've taken things to a project concept level, and the next phase of their thinking is about delivering that and doing it on something real. This is the opportunity to do that. We're looking at demonstrations that involve trial builds or equivalent, using one or more of the technologies or processes or techniques from phase 1 of our program. And again, I'll get to that in terms of the eligibility criteria. And these techniques, we believe, should be applicable to the build, maintenance and decommissioning of nuclear sites as well as future technologies. We're leaving this pretty wide in terms of setting out the scope. If you can prove that in one of those areas you can use this, then put in a bid. Taking the scope forward. The demonstrator has got to be able to exhibit the anticipated benefits of advanced manufacturing, in that it's got to be able to bring down the price, and it's got to be able to work in an environment that is regulated. Each of the demonstrator projects has got to encompass at least one of the phase 2 work areas. Now, I've listed them out in short form there. Again, in the guidance, our colleagues at NIRO have worked with us to provide a lot more information on what we mean by those work areas, but you need to be sitting within at least one of those. So moving on to the eligibility criteria. This is kind of the how do you get through the front door. The first 3 of these are pretty much the key to our grant call. You have to develop a technology, process, or one of the outputs from phase 1 to its next level. Now, you can bring other technologies, other processes, other ways of doing things into your bid, but you must demonstrate and take forward at least one of the things that came out of phase 1. This is why there is space for coffee later, because all of those people that you've just seen give a presentation, you must have one of those teams or one of their outputs involved in your process. If you have more than one, that is great. In fact, the weighting criteria that we are setting out will give preference to organisations and projects that have more than one, in fact, all of them. So the more you can get in, the better your weighting. You must be able to show a reduction in cost over a traditional method. This isn't just doing the stuff. You need to be able to show as part of the bid that you can actually bring down the cost of nuclear by bringing these things together and integrating them. A lot of what Jonathan has just said about taking all of these projects and having an end game is what we're after. And you must have, and this is the slightly fuzzy grey area one, the ability to meet regulatory standards. Now that doesn't mean this has to be done on a regulated site. It doesn't mean you have to bring the regulator in. But whatever you kick out at the end has to be regulatable. Now in your bids you can put how you intend to achieve that and how you intend to be able to say to us this is regulatable. It can involve using the regulator, it can involve using operational experience, but it has to be regulatable. Don't design something that is so outlandishly weird that the regulator is going to walk in the room, take one look at it and go away. And the project location, it must be done in the UK. As I said, this is a grant competition, so it gives us a bit more flexibility in the things that we can set out. Moving on with the eligibility criteria, there's no set limit to how long your project takes, but we will only provide funding up until March 2021. That's the end of our spending review period. At that point, I don't know how much budget I have after that, but I have £20 million up until that point. Because it's a grant, we're working within European state aid rules at the moment, and under the GBA general block exemptions, we can provide up to £10 million per project. So bids of up to £10 million for the money you want to us. We could get 2 very large bids, we could get lots of very small bids. We are open to everything. And then we have the aid intensity. GBA sets out, sorry for those at the back, but I can read this out, very strict guidelines on the amount of money government can put in. So this is where you are going to require matched funding from a non-public source. Generally speaking, we have made an assumption that the consortia or the bids being put forward will involve one or more large enterprises. It doesn't have to be, it can be completely small enterprises, but on the assumption that there is one or more large enterprises, the maximum amount of grant intensity we can provide for a collaborative project where the results will be disseminated is 65% of the total eligible costs. Now, there's a lot more information in the grant guidance documents about what eligible costs are, and the European Union state aid rules also provide chapter and verse on eligible costs. It's not just money, it's facility access, it's time and cost, it's people. There are a number of tunes that can be played with eligible costs, so have a look at those, work out what your eligible costs are, and then work out how we are up to £10 million is 65% of that grant intensity. Now, if you go down to only small enterprises with collaborative, you can have up to 80% of the project costs. But again, we've made a standing assumption up front that there will be one or more large enterprises as defined under the state aid regulations. And then who can apply? We're happy to accept bids from single companies and from consortia. Members of the project team must or can be UK registered private sector companies. You can be SMEs, you can be large, you can be small, don't really mind. And you can apply on your own or as part of consortia with other organisations. You can lead or you can be single applicants. UK academic, research, public, third sector or community organisations can participate as long as they are doing so with a private sector organisation. The only constraint there is you cannot be sole applicants to this competition. You can lead, but you can't be sole applicants. So if you're a university or a research organisation, you need to bring a UK registered private sector company with you, but we are happy for you to be the lead bidder. International organisations are more than happy to participate as consortium members with UK organisations as set out above. The constraints on international members are that they cannot be sole applicants and they cannot be the project leads. But as long as they're in a consortia with UK organisations, we are happy to accept those in the bids. And the project team must include an organisation with the capability to deploy the outputs of the demonstration, i.e. someone must be able to take the outputs of this and go and use it repeatedly in the real world. Bit down to applications. So, applications are invited to be submitted by the 8th of March, electronically. There is an application form. So rather than in a procurement world where we set sort of a page limit, there is for grants a quite specific application form which you will find on the website. That includes sections with character limits. So please abide by the character limits, otherwise you will be ineligible for the approach. We are looking for application forms, for partner detail forms, if there is more than one of you in the consortia. There's a wonderful little finance spreadsheet on there where you set out all of the money you intend to spend. We're looking for a Gantt chart or similar tool to be able to show us how you intend to do the work. And we need you to fit in that. In terms of additional information, we have to put this caveat up. You can send us as many annexes as you want, with as many pretty pictures in as you want, but do not assume that we will read those when it comes to doing the actual assessment. We will read the application form. The reason for this is if we only got 2 applications in, we are likely to start looking at the annexes for interest. If we get 40 to 50 to 60 applications in, we only have a finite number of resources, so we are going to focus down on the application forms. To give you an idea of the timelines we're looking at, the documents will go live on the government website at 5 o'clock today, or so I am informed. Usually it would take them a little longer, but our digital team have done a blinder, and they're aiming to get the documents out today. Applications, as I said, to Nuclear Innovation at BEIS by the 8th of March, and the close on the 8th of March. We will then assess the applications using a number of internal staff and third-party assessors, and we hope to have our assessment completed by the 29th of March, because nothing else important appears to be happening that week, so I'm sure everything will be fine. We're intending to give the grant awards out on the 6th of May. The reason for the length of time between us announcing who's got the money and actually giving the money is, as this is not a procurement, a lot more detail has to go into the grant offer letters. It's not quite as simple as we put out the ITT, you put in a bid, we staple them to the back, and that's your contract. Grant offer letters are a little bit more complicated. If you haven't dealt with a grant before, find someone over coffee that has, because there are certain nuances and certain ways that you go forward. For instance, you're only paid for, or you're only given money for, the things you do in the grant specification area. If you've done work before that, you can't have money for it out of this grant. If you do work after that, this grant doesn't apply. That is pretty much everything I've got on this. As I said, the documentation is going to be going live on the website later today. Download it, read it. If you've got any questions, either today or in the future, you can ask now or drop them to Nuclear Innovation at BEIS. The questions from today and anything we receive over the period, we will start putting into a Q&A session, a Q&A pack that will go online with the grant applications. So keep an eye on that website. And the only other thing to say is it's now up to you guys to go out and set up those consortia, talk to the people from phase 1, decide what it is you want to do next. This is probably one of the most flexible grant competitions we've launched in SICE within BEIS. We're not really setting as many criteria as we would normally. As I said, it's demonstrate something, show that it's cheaper, involve somebody or something from phase 1 and make it regulatable. Outside of that, the world is your oyster. I heartily recommend you all go and talk to each other, and as everybody else previously, Rotherham, Sheffield on Wednesday might be an equally good place to learn what's gone on from phase 1 and what you might want to work with in phase 2. I'll leave it at that.
Okay, thanks, Si. I'm pretty confident there might be one or two questions before you do. No. Pretty confident. Is there any burning questions for Si, or are you keen for more coffee and having a chat? I thought there might be. Hang on a minute, please.
I'm interested to know how solid those dates are.
You will note that we are launching this today. When we have a government and when things are there. So, the future is fairly uncertain. But my intention is the fact that this is launched today, this is an ongoing process. Had I launched this, say, last Friday, then I wouldn't know if it was carry on. But yes, our intention is this goes out today, this holds. Unless something really bad happens, yeah, those dates are as solid as I can guarantee them at this moment in time.
Any more?
Hi, just a quick check on the state aid. So there were two different levels of aid intensity for the organisations that you flashed up before. There it is. So on the second sort of higher levels of aid intensity, so that's for companies that work with effectively a research organisation or something that can disseminate the results publicly. Is that correct?
Yes.
Okay, so ourselves, hello, Nuclear MRC, or other universities, plug. But yeah, okay, just checking. Thank you.
Yeah, if you want a higher grant intensity, go work with someone from the research side, and that's fine.
Okay. Any more? Chris, could you? Thank you.
Yeah, thanks. It's Simon McCorden from TWI. Just to clarify again on this screen, so you're saying there'll be two projects or programmes funded with a maximum of £10 million?
We are saying there is a £20 million pot of money. We will look at the bids that come in, we will rank them, and then we will fund going from the top of the ranking until we run out of money. Now, the maximum bid you can put in is £10 million. So if the top two on the ranking table are £10 million, we'll fund two. If the top 10 on the ranking table are much smaller, then we'll fund 10.
Thank you. Any more? Right. I think we're done. We're done. Thank you. Thanks, Si. Okay. End of show. Okay. All that remains for me to do is to remind you that there's coffee outside. And we've got plenty of time. I think we've got this facility till 4:30, so I'm sure you won't be kicked out. The next thing is to remind you that the information will be sent out as soon as possible, definitely by the end of this week. So all the links to all the information, all slides, will be with you before the end of the week. And the final thing to say is thank you all for coming. I know it was very short notice, and it was great to see a full room of people. So thank you once again, and safe journey. Thank you.